Hello there, and welcome to Physics with William, where curiosity gets cozy, science takes the scenic route, and the universe is allowed to be enormous without needing to be in a hurry. Tonight, we are turning toward the brightest object in our sky. The one thing you're never supposed to stare at, never supposed to touch, and certainly never supposed to send a delicate little spacecraft toward, unless you have a very good heat shield and a rather fearless engineering team. We're talking about the sun, not as a yellow circle in a child's drawing, not as a pleasant patch of warmth on the carpet, and not as the thing that ruins your plans when you forget sunscreen, but as a real star, a churning, magnetic, boiling, stormy sphere of plasma that holds the solar system together and reaches out across billions of miles with invisible influence. And for almost all of human history, the sun was something we could only observe from a safe distance. We could watch it rise. We could measure its light. We could feel it on our faces. We could write myths about it, build calendars around it, and argue about whether it had spots on it without being accused of ruining the sky. But touching it, even with a machine, sounded less like science and more like the sort of thing a very confident moth might suggest after a long evening near a lamp. And yet, that is exactly what humanity has now done. NASA's Parker Solar Probe became the first spacecraft to pass through the sun's upper atmosphere, the corona, and sample particles and magnetic fields there, a moment NASA described as the first time a spacecraft had touched the sun. Now, of course, no one reached out a hand and patted the sun gently on the shoulder. There was no tiny astronaut in oven gloves knocking politely on the surface of a star. The word touched is being used in a scientific sense, but it is still a powerful one. The sun does not have a hard surface like Earth does. There is no glowing floor where a spacecraft might land and say, well, this seems warm. The sun is made of plasma and layered atmospheres, with gases and charged particles flowing, rising, twisting, and escaping into space. To touch the sun, in this case, means to cross into the region where solar material is still bound to the star, to enter the outer atmosphere where the sun's own magnetic fields and particles still rule the environment. It means moving from studying the sun as something distant to studying it from inside its atmosphere, like going from watching smoke above a candle to carefully drifting through the smoke itself, though in this case the candle is a star and the smoke can knock satellites out of service. That simple phrase, NASA touched the sun, carries a quiet kind of astonishment. It sounds almost impossible because in ordinary life, the sun is the symbol of distance. It is always there, but always unreachable. It paints the morning on your curtains, warms the roof tiles, fades old photographs, grows forests, powers weather, and gives every breakfast table shadow a direction. It is familiar in the way a clock is familiar, or a window, or the kettle that somehow waits until you leave the room before it finally boils. But familiarity can make us forget how strange something is. The sun is not merely a bright object. It is a star close enough to shape every breath of life on Earth. Every green leaf is, in a sense, a little solar historian, storing sunlight in chemical form. Every gust of wind, every ocean current, every warm afternoon, every season, every harvest, every ancient sundial, and every modern solar panel belongs to the story of this one star. And yet, for all that dependence, there have been deep mysteries about the sun that scientists could not solve by looking from Earth alone. One of those mysteries is almost wonderfully irritating. The sun's visible surface, the part we usually imagine when we picture the glowing disk, is extremely hot. But its outer atmosphere, the corona, can be far hotter, reaching millions of degrees. That should feel odd. If you sit beside a fireplace, you expect the air to grow cooler as you move away from the flames. You do not expect the room 10 feet from the fire to become dramatically hotter than the bricks right beside it. And yet the sun seems to do something like this. The corona, the faint outer crown seen during total solar eclipses, is much hotter than the surface below it. Scientists have been asking why for many decades. They have suspected that magnetic fields, waves, and explosive rearrangements in plasma might help carry energy upward and outward. but suspicion is not the same as standing in the region itself and measuring what is actually happening. Parker Solar Probe was designed to do what distant telescopes cannot do. It flies through the very place where the clues are being created. It is not merely watching the storm from a hilltop. It is taking measurements in the wind. This is why the mission feels so historic. Space exploration often gives us images of faraway places, a rover crossing red Martian dust, a telescope looking deep into ancient galaxies, a probe sailing past icy moons. These are all extraordinary, but Parker is different because it is not travelling outward into cold distance. It is diving inward, toward the furnace at the centre of our local cosmic neighbourhood. Since its launch in 2018, Parker Solar Probe has used repeated flybys of Venus to reshape its orbit and move closer and closer to the Sun, eventually reaching record-breaking approaches measured in only a few million miles from the solar surface, which is very close indeed when the object in question is a star. On December 24th, 2024, NASA confirmed that Parker survived a record close pass just about 3.8 million miles above the solar surface while travelling about 430,000 miles per hour, faster than any human-made object had ever moved. That is the sort of speed that makes ordinary travel seem deeply unserious. A long car journey suddenly feels less like transportation and more like a polite suggestion. And still, even with numbers like that, the real wonder is not simply that Parker moves quickly or gets close. The wonder is that it survives. A spacecraft near the Sun has to deal with extreme heat, intense light, energetic particles, and an environment that is not especially interested in being hospitable. Parker is protected by a heat shield made to keep its instruments in shadow, because the difference between surviving and becoming a rather expensive glowing memory is partly a matter of always knowing which way is sunward. The spacecraft has to point itself with exceptional care, keeping its protective shield between its sensitive body and the blazing star. In that sense, Parker is a little like someone crossing a desert with one perfectly placed umbrella, except the desert is made of radiation and plasma, and the umbrella has to work while moving faster than anything humanity has ever built. There is something almost charming about that, in a very serious engineering way. This tiny machine, built by human hands, launched from Earth, guided by mathematics, powered by careful planning, is skimming through the outer atmosphere of a star while keeping itself tucked behind its own little patch of shade. The discoveries from this mission matter because the Sun is not simply a distant object of scientific interest. It is active. It has weather. Not weather like rain on the windows or a grey Tuesday afternoon, but space weather, driven by magnetic fields, charged particles, solar wind, flares, and huge eruptions that can travel outward through the solar system. Most of the time, Earth's magnetic field protects us beautifully. It wraps around our planet like an invisible shield, guiding many incoming particles away and helping turn some of them into auroras near the poles. But strong solar storms can still affect modern technology. They can disturb radio communication, interfere with satellite operations, confuse navigation systems, and in severe cases induce electrical problems in power grids. It is a peculiar feature of modern life that a storm beginning on the Sun can eventually matter to someone trying to use a phone map, fly a plane over a polar route, operate a satellite, or keep electricity flowing through long transmission lines. The Sun may be 93 million miles away on average, but it is not detached from us. It is not merely scenery, it is a working part of our technological world. That is one of the reasons Parker's journey is not just symbolic. By studying how the solar wind is born and accelerated, by measuring magnetic fields close to the Sun, and by flying through the corona itself, the spacecraft is helping scientists understand the conditions that lead to space weather before that weather spreads through the solar system. NASA's mission description emphasizes that Parker is designed to study the corona, the solar wind, and energetic particles by sampling the Sun's atmosphere directly rather than only observing from afar. This is like learning about a river by placing instruments near the spring rather than only watching the water after it has already travelled across the landscape. By the time solar wind reaches Earth, it has mixed, stretched, collided and evolved. The original fingerprints can be faint. Parker goes closer to the source, where the first signs are clearer, where the magnetic structures are fresher, where the sun's atmosphere is still speaking in its own immediate voice. And there is something gently humbling about realizing that the sun, which feels so steady from the ground, is in fact full of motion. To us it rises and sets with dependable rhythm. It seems constant enough that we use it as a symbol of certainty. Tomorrow the sun will rise. There is comfort in that phrase. But seen through the eyes of solar physics, the sun is restless. Its surface bubbles with enormous convection cells. Its magnetic fields twist, snap, and reconnect. Dark sunspots come and go. Loops of plasma arch above the surface. Streams of charged particles pour outward. Sometimes the sun releases powerful bursts of radiation or hurls vast clouds of material into space. It is steady in the long sense, generous in the life-giving sense, and yet incredibly dynamic from moment to moment. It is less like a lamp and more like a living weather system made of plasma, magnetism and heat. Not alive, of course, though one could forgive our ancestors for imagining it that way. If you had no telescope, no spacecraft and no physics textbook, but you saw the sun decide the seasons and command the day, you too might be tempted to give it a personality. Before Parker, we had already learned a great deal about the sun. Telescopes on Earth and in space had watched it in visible light, ultraviolet light, X-rays and other wavelengths. Solar observatories had mapped its magnetic fields, tracked eruptions, and recorded the dance of sunspots across solar cycles. The Solar and Heliospheric Observatory, the Solar Dynamics Observatory, and many other missions had given scientists astonishing views. But there is a difference between looking at the ocean from a cliff and lowering an instrument into the waves. Remote observation can tell us a tremendous amount, but some questions require direct contact with the environment. Parker gives scientists measurements of particles, magnetic fields, electric fields, waves, dust, and images from closer than any previous mission. It is a laboratory sent into a place no laboratory on Earth can truly reproduce. We can imitate parts of solar physics in experiments and simulations, and those are powerful tools, but the sun itself remains the final authority. It is the original source material. What makes this story especially satisfying is that the Parker Solar Probe is named for Eugene Parker, the physicist who predicted the solar wind in the 1950s. At the time, the idea that the sun constantly releases a stream of charged particles into space was not immediately embraced by everyone. It was a bold proposal, and like many bold proposals in science, it had to pass through skepticism before becoming part of the accepted picture. Decades later, a spacecraft carrying his name flew toward the very wind he helped explain. NASA notes that this was its first mission named for a living person, honouring Parker's foundational work in heliophysics. There is a lovely completeness in that. A human mind imagines an invisible flow from the sun. Years pass, instruments improve, rockets grow more capable, engineers build a spacecraft, and then that spacecraft sails into the region where the invisible flow begins, carrying the name of the person who first saw it clearly in mathematics and physical reasoning. So tonight, as we settle into this story, it may help to hold two ideas together. The first is the grand idea, the headline idea, the almost mythical idea that humanity has touched the sun. That is the kind of phrase that belongs beside sailing beyond the horizon or stepping onto the moon. It speaks to exploration in the old sense, the urge to go closer, to test the boundary, to ask whether impossible simply means not yet. The second idea is quieter and more practical. Parker is not just a symbol, it is a working spacecraft gathering measurements that may help us understand the corona, the solar wind, solar storms, and the chain of events that can eventually affect life and technology on Earth. It is a mission of wonder, certainly, but also of preparedness. The more we understand the sun, the better we can live with it. And that brings us to a small question for you, wherever you are listening from. When you think of the sun, what comes to mind first? Is it sunrise through a window, the warmth of a summer afternoon, a memory of squinting at the sky, the glow on buildings near evening, or simply the practical thought that you really should have brought sunglasses? And where in the world are you tonight, under this same star, perhaps in morning light, perhaps in late evening, perhaps in the quiet middle of the night with the room dim and the day finally slowing down? It is a strangely comforting thought that everyone on Earth lives by the same sun but not at the same hour. Somewhere it is breakfast, somewhere it is dusk, somewhere someone is stepping into bright heat, while someone else is closing the curtains against the dark. The star is shared. The moment is personal. If you find this gentle journey soothing, or if you simply enjoy the idea of learning about a spacecraft that decided the best way to understand the sun was to fly almost directly into its atmosphere, I would be very grateful if you gave the video a like, subscribed, or left a quiet note about where you are listening from. It helps this little corner of calm science reach others who might enjoy drifting through the universe without being startled by it. And as always, I do hope this is interesting enough to keep you company, but not so exciting that it keeps you awake. The sun can be dramatic, but we will approach it carefully, with a soft voice, a steady pace, and absolutely no need to rush toward a star faster than Parker already has. So, settle in. Let the day loosen its grip a little. Let the thought of the sun become not harsh or glaring, but distant, steady, and immense. Tonight we're going to follow a spacecraft no larger than a small car as it falls again and again toward the heart of the solar system. We will see why the sun's outer atmosphere is so strangely hot, how streams of particles become the solar wind, why magnetic fields can twist into storms, and how a machine built on Earth can survive in a place where ordinary materials would fail almost instantly. We will begin not with the closest approach, nor with the heat shield, nor even with the corona itself, but with the old human habit of looking upward and wondering how close we could ever really get to the light that makes our world possible. Long before a spacecraft ever carried instruments into the sun's outer atmosphere, long before engineers designed a heat shield that could survive near a star, and long before anyone knew that the sun was made of plasma, people looked upward and understood one thing very clearly. The sun mattered. It was not optional scenery. It was the great clock, the great lamp, the great farmer, the great weather maker, the difference between freezing and growing, between day and night, between losing your way and finding the shape of the land again. It told ancient people when to plant, when to harvest, when animals might migrate, when rivers might swell, and when shadows would shrink beneath their feet at noon. The sun did not need a telescope to become important. It announced itself every morning with the simplest possible argument: here I am again. For early human beings, the dream of reaching the sun would not have begun as engineering. It would have begun as attention. Watching the eastern horizon, noticing that sunrise moved slightly across the year, seeing that the longest days and shortest days returned with patient regularity, marking stones, posts, doorways, and temple alignments so that light would arrive in a certain place on a certain morning. This was not space exploration in the modern sense, of course, but it was the first quiet step towards solar science. Before we could fly toward the sun, we had to realize that it could be studied. Before we could send a probe into the corona, we had to become the sort of species that kept asking the sky to explain itself. The first solar observatories were not satellites or domes with polished mirrors. They were landscapes shaped by patience, a standing stone casting a shadow, a carefully placed opening admitting sunlight at dawn, a line scratched into bone or rock to track the passing days. The sun was the most reliable object in ordinary experience, and yet it was also strangely unreachable. You could feel its warmth without touching the fire. You could see its disk but not approach it. You could rely on it without understanding it. That combination, familiar and unreachable, practical and mysterious, is one of the reasons the sun took such a strong hold on human imagination. It was both daily and divine, both useful and frightening. It could ripen grain, dry rivers, burn skin, and vanish during an eclipse as if the world had briefly misplaced its centre. Eclipses must have been especially powerful. Imagine living in a world without astronomy textbooks, without printed calendars, without anyone calmly saying that the moon is passing between Earth and the sun. The day begins normally. Birds call, people work, shadows lie where they should. Then the light thins, the air changes, the sun is bitten away. The familiar world becomes unfamiliar. Even now, with all our knowledge, people who stand under a total solar eclipse often describe the experience as unsettling, beautiful, and difficult to explain. In the deep past, such an event would have seemed like a message from the heavens, or a warning, or a wound in the day itself. Yet eclipses also gave humans something precious. They forced careful watching. They encouraged prediction. They showed that even the most dramatic events in the sky followed patterns. Fear, over time, became measurement. As civilizations grew, the sun became a central figure in calendars and architecture. Ancient Egyptians used solar cycles to organize agriculture around the flooding of the Nile. In many cultures, temples and monuments were aligned with sunrise or sunset at important times of year. The sun was not just a bright object. It was built into society. It was a schedule written in light. Priests, farmers, sailors, rulers, and ordinary families all lived under its timing. Long before anyone could describe nuclear fusion, the sun had already become a form of order. It was how the year made sense. Then came the slow and sometimes uncomfortable process of changing where we thought the sun belonged. For a long time, many educated traditions placed Earth at the center of the cosmos, with the sun and planets moving around it. That arrangement felt natural from the ground. After all, Earth does not feel as though it is moving. The sun appears to rise in one direction and sink in another. The stars seem to wheel around us. Common sense, which is often useful for finding your shoes but less reliable for mapping the universe, suggested that we were still and everything else was circling. But patient observation began to loosen that picture. Ancient Greek thinkers explored different models. Later astronomers measured planetary motion with increasing precision. Eventually, the idea that Earth moves around the sun became not just a possibility, but the foundation of modern astronomy. That change was more than a technical correction. It altered humanity's relationship with the sun. The sun was no longer merely the bright traveller across our sky. It became the centre of our local system, the gravitational anchor around which Earth and the other planets move. In this view, we were not the central platform of creation with the sun serving as a lamp. We were one world among others, circling a star. That can sound humbling, and it is, but it is also a gift. Once the sun became a physical body in space rather than a mythic fixture, it became something that could be investigated, not worshipped from a distance only, not feared during eclipses only, but questioned. The telescope deepened that questioning. When early telescopic observers turned their instruments toward the sun, carefully and not always safely by modern standards, they discovered that the solar surface was not perfect. Sunspots appeared as dark marks moving across the disk. To some, this was shocking. The heavens had often been imagined as pure and unchanging, while Earth was the place of decay and mess. But the sun had blemishes. It changed. Its spots formed, shifted, and disappeared. Galileo and other observers helped show that sunspots could be used to infer the rotation of the sun. The star was not a fixed golden emblem. It was a turning physical object with activity on its face. That realization matters because it began the long transformation of the sun from symbol into system. A system has parts. It changes with time. It can be measured, compared, and modelled. Sunspots were not decorative flaws, they were clues. Later scientists would learn that they are linked to intense magnetic activity and that their numbers rise and fall over a cycle of roughly 11 years. But even before the magnetic explanation, the simple fact of sunspots showed that the sun had weather of its own. Not weather like rain clouds and puddles, but patterns, disturbances, and cycles. The sun was not merely shining, it was doing things. The next great step was learning to read sunlight itself. When scientists began splitting sunlight into its colours, they discovered dark lines in the solar spectrum. These lines were not random. They were fingerprints of elements absorbing particular kinds of light. This opened an astonishing possibility. Humans could learn what the sun was made of without going there. A beam of sunlight passing through a prism and then into careful instruments could carry information across 93 million miles. It was like receiving a letter from a star, written not in ink but in missing colours. Spectroscopy turned sunlight into evidence. It showed that the sun was physical matter, governed by the same kinds of laws as matter on Earth. This was a quiet revolution. The sun had once seemed unreachable, because no hand could touch it, and no traveller could sail there. But science discovered that touch is not the only way to know something. Light carries news, shadows carry timing, motion carries mass, a spectrum carries chemistry. Every observation became a way of reaching without moving. Still, there remained a difference between studying the sun's message after it arrived at Earth and going closer to the place where that message began. The old dream did not disappear. It simply became more precise. During total solar eclipses, another clue became visible. Around the darkened disk of the moon, observers could see the sun's corona, a pale outer glow usually hidden by the overwhelming brightness of the solar surface. It looked delicate, almost ghostly, but it was not delicate in the physical sense. It was the outer atmosphere of a star, shaped by magnetic fields and filled with hot, thin plasma. For a long time, the corona could be studied best during eclipses, which are brief, rare, and inconveniently unwilling to happen in the same observatory every Tuesday. Scientists travelled to distant places, carrying instruments, hoping clouds would behave themselves, which clouds do not always do. Solar science, in that era, sometimes depended on a few minutes of darkness and a great deal of luck. As instruments improved, the sun became stranger rather than simpler. Scientists learned that the visible surface was hot, but that the corona was far hotter. This was deeply puzzling. Ordinary intuition says that distance from a heat source should bring cooling, not heating. Yet the sun's outer atmosphere reaches temperatures far above those of the surface beneath it. This became known as the coronal heating problem, one of the major unsolved puzzles in solar physics. To solve it, scientists needed to understand how energy moves through the sun's outer layers, especially through magnetic fields and waves in plasma. That meant the corona was not just beautiful during eclipses, it was a crime scene, if one may use a slightly dramatic phrase for a very hot atmosphere. Something was heating it, and the evidence was scattered through motions, waves, particles, and magnetic structures. Another mystery emerged as scientists studied the space between planets. Earth is not sitting in empty stillness. It is immersed in a stream of charged particles flowing outward from the sun. This stream is called the solar wind. Eugene Parker predicted this continual outflow in the 1950s, arguing that the sun's hot corona should expand outward into space. The idea was not instantly welcomed because science, quite reasonably, likes bold ideas to bring evidence with them. But later spacecraft measurements confirmed the solar wind, and Parker's insight became central to heliophysics, the study of the sun and its influence throughout the solar system. NASA later named Parker Solar Probe after Eugene Parker, making it the first NASA mission named for a living person. This was a turning point in the human dream of reaching the sun. The sun was no longer only the object shining in the middle. Its atmosphere extended outward. Its wind filled interplanetary space. its magnetic influence shaped a vast region around the solar system. In a sense, we had been inside the sun's extended influence all along. Earth moves through the heliosphere, the immense bubble carved out by solar wind. We do not live beside the sun in a detached way. We live within the territory it creates. That makes the idea of touching the sun even more interesting. It is not simply a journey to a glowing ball. It is a journey inward through layers of influence, toward the place where the wind is born and where the corona still belongs magnetically to the star. The space age changed the dream from observation to approach. Rockets gave scientists a way to place instruments above Earth's atmosphere, where ultraviolet and X-ray light from the sun could be measured more clearly. Earth's atmosphere protects life wonderfully, but it also blocks many forms of solar radiation that scientists want to study. This is one of those situations where nature is being helpful and inconvenient at the same time, rather like a very protective friend who keeps covering your notebook because the information might be dangerous. Space-based solar observatories allowed researchers to see the sun in new wavelengths, revealing flares, loops, eruptions, and structures that ordinary visible light could not show. Early satellites and probes began measuring particles and magnetic fields in space. They confirmed that the solar wind was real and variable. They showed that solar storms could disturb Earth's magnetic environment. They gave scientists a wider view of the Sun-Earth connection. But the dream of going very close to the sun remained difficult. The challenge was not only heat, although heat is certainly rude enough on its own. The deeper challenge was orbital motion. Earth is moving rapidly around the sun, and a spacecraft launched from Earth inherits that sideways motion. To fall close to the sun, a spacecraft must shed a great deal of that motion. Oddly enough, going to the sun is not as simple as pointing downward and letting gravity do the rest. Space does not reward common sense quite as often as one might hope. This is why missions toward the inner solar system often use gravity assists. A spacecraft can fly near a planet and use that encounter to change its path and speed. Parker Solar Probe uses repeated flybys of Venus to gradually adjust its orbit and bring itself closer to the sun. This method is elegant, patient, and slightly like using a moving planet as a cosmic steering handle. The probe does not simply dive once and hope for the best. It loops around again and again, each time reshaping its orbit, each time moving into more extreme territory. That slow tightening of the path is part of the mission's brilliance. To reach the sun, humanity did not simply build a fast machine. It learned how to borrow careful nudges from another world. Before Parker, other missions had already ventured closer than Earth and studied the solar environment. The Helios probes, launched in the 1970s by the United States and West Germany, travelled inside Mercury's orbit and set important records for close solar study. Later missions such as Ulysses studied the Sun from unusual angles, including over the solar poles. The Solar and Heliospheric Observatory gave long-lasting observations of the Sun and helped monitor solar activity. The Solar Dynamics Observatory provided detailed, continuous views of the Sun in multiple wavelengths. Each mission added another layer. Each one made the Sun less mysterious in one way and more interesting in another. That is often how science behaves. It answers a question, and then, with a completely straight face, hands you 3 better questions. Yet none of these earlier missions entered the corona itself in the way Parker Solar Probe eventually did. That boundary is important. NASA reported that Parker passed through the Sun's upper atmosphere, the corona, and sampled particles and magnetic fields there, marking the first time a spacecraft had touched the Sun. During that encounter, the spacecraft moved in and out of the corona several times, revealing that the boundary is not a smooth, simple shell, but has structure, with spikes and valleys shaped by solar activity. To understand why that is meaningful, picture standing at the edge of a forest. From a distance, the treetops may look like a smooth green surface, but if you walk closer, you see gaps, branches, slopes, clearings, and tangled edges. The boundary is real, but it is not simple. Parker found something similar with the Sun's outer atmosphere. The edge of the corona, called the Alfvén critical surface, is not a neat sphere sitting politely around the Sun. It is wrinkled and uneven, shaped by the magnetic and plasma conditions below it. Inside that boundary, waves and particles can still travel back toward the Sun. Outside it, the solar wind has effectively broken free and flows outward. Crossing that boundary is not like passing through a wall. It is more like entering a region where the rules of connection change. The dream of reaching the Sun, then, has become less like trying to land on a fiery surface, and more like trying to enter a moving atmosphere and understand where the Sun stops holding its material close. That is a more subtle dream, but also a more scientific one. A child might ask whether we can touch the Sun. A physicist asks what counts as touch when the Sun has no solid ground, when its atmosphere fades outward, when magnetic fields connect regions across enormous distances, and when plasma can behave in ways ordinary air never does. Parker's achievement gives that old, simple question a careful answer. Yes, in the way that matters for solar physics. We have crossed into the Sun's atmosphere. We have measured it directly. We have let instruments feel what telescopes could only infer. It is worth pausing on the emotional side of this. Humans are small, soft creatures from a planet with rain, soil, kitchens, libraries, and socks that vanish without explanation. The Sun is a star. The scale difference is almost silly. If the Sun were only an enemy, we would hide from it. If it were only a tool, we would use it without wonder. But it is both powerful and necessary, dangerous and life-giving, ordinary and almost impossible to comprehend. The long dream of reaching it is not really about conquest. We are not conquering the Sun by sending a probe into its atmosphere. The Sun does not notice us in that way. It is not impressed. It has been fusing hydrogen for billions of years, and is unlikely to pause because a small machine from Earth flew past with excellent instruments. The achievement belongs to us not because the Sun is defeated, but because our understanding has grown brave enough and careful enough to go closer. That combination of bravery and care is important. The history of solar study is not a straight line from ignorance to mastery. It is a slow accumulation of techniques, watching shadows, predicting eclipses, tracking spots, splitting light, launching telescopes, measuring the solar wind, designing heat shields, calculating gravity assists, protecting electronics, building instruments that can gather useful data in an environment that would destroy ordinary machinery. At every stage, the dream became more practical, not less wondrous, but more exact. Wonder does not vanish when details arrive. In science, details are often what keep wonder from floating away. And this is where the story begins to turn toward the little spacecraft itself. The human dream of reaching the Sun required myths and calendars, telescopes and spectra, daring theories and patient measurements. But eventually it also required hardware. It required carbon composite shielding, autonomous guidance, instruments tucked safely behind shade, and a mission plan that could survive years of increasingly close passes. It required a spacecraft able to move at record-breaking speed and still behave with the discipline of a careful laboratory. NASA confirmed that Parker made a record close approach on December 24, 2024, passing about 3.8 million miles above the solar surface while travelling about 430,000 miles per hour, then later signalling that it had survived the encounter. Those numbers are impressive, but they are not the whole story. The whole story is that for thousands of years, people lived by the Sun, feared it, worshipped it, measured it, argued about it, studied it, and slowly learned enough to send something toward it. Not a chariot, not a mythic hero, not a winged figure flying too close with unfortunate results, but a spacecraft named for a scientist who understood that the Sun was constantly breathing particles into space. The old dream did not arrive as a single dramatic leap. It arrived as a long chain of careful human attention, each generation handing the next one a better question. And now, with that long path behind us, the next part of the story becomes much more physical. Because dreaming of the sun is one thing, building a machine that can survive near it is another matter entirely. Parker Solar Probe had to be designed for a place where sunlight is not just bright but intense, where the spacecraft has to hide behind its own shield, where a slight mistake in orientation could expose delicate instruments to conditions they were never meant to endure. The old observers watched the sun from fields, temples, ships, observatories and mountain tops. Parker would have to watch it from inside the glare, close enough that the sun no longer feels like a disk in the sky, but like the overwhelming environment through which the spacecraft is flying. To understand Parker Solar Probe properly, it helps not to picture it as a grand silver spaceship from a film poster, gliding heroically through space with enormous windows and dramatic engines. Parker is far stranger and more practical than that. It is a compact scientific machine, built with the very specific purpose of surviving a place where ordinary spacecraft design begins to look wildly optimistic. It is roughly the size of a small car, not a palace, not a rocket ship with hallways, not a crude vessel with someone nervously asking whether the air conditioning is still working. It is a careful arrangement of instruments, wiring, computers, antennas, solar arrays, cooling systems, and one extremely important heat shield, all designed around a single basic rule. Keep the sensitive parts in the shade. That may sound almost too simple for a mission to the sun, but simplicity is sometimes where the cleverness hides. Parker Solar Probe does not survive because every part of it is equally exposed and equally indestructible. It survives because the spacecraft is built like a creature that knows where danger is coming from. The sun is always on one side during the most intense parts of the encounter, and the spacecraft keeps its protective shield facing that direction. Behind that shield, in a narrow region of shadow, the electronics and most of the instruments can remain at temperatures that are not very different from a warm room on Earth. In front of the shield, sunlight is fierce enough to turn many materials into a very expensive lesson. Behind it, the spacecraft can continue thinking, measuring, recording, and quietly doing the work it was sent to do. This shield is called the Thermal Protection System, which is a very formal name for what is essentially Parker's survival umbrella. It is made from carbon-based materials, including carbon composite faces with a carbon foam core between them, and it is coated on the sun-facing side with a bright white material that helps reflect as much sunlight as possible. NASA describes the shield as about 8 feet across and 4.5 inches thick, weighing only about 160 pounds, while still being able to protect the spacecraft as the sun-facing side reaches temperatures of thousands of degrees Fahrenheit. During close approaches, the shield can face temperatures around 2,500 degrees Fahrenheit, while the spacecraft and most instruments behind it remain near room temperature. That contrast is the heart of the mission's engineering. On one side, a surface hot enough to ruin steel. On the other, instruments kept cool enough to function. It is a little like holding a biscuit behind a frying pan and expecting the biscuit to remain calmly edible, while the pan faces a furnace. Except the biscuit is a spacecraft, the furnace is the sun, and everyone involved would prefer not to explain to NASA why the biscuit has stopped transmitting. The heat shield is not simply a thick wall. It is an engineered compromise between strength, lightness, insulation, reflectivity, and shape. It has to be light enough to launch, strong enough to survive, and precise enough to cast the right shadow over the spacecraft body. A shield that is nearly good enough would not be good enough at all. Near the sun, nearly in the shade, is just another way of saying exposed. Parker also needs to manage something that feels almost unfair. It must use sunlight for power, while also hiding from sunlight to survive. Solar panels are wonderfully useful near Earth, where sunlight is abundant but not overwhelming. Near the sun, there is so much sunlight that the problem changes. Instead of asking how to collect enough energy, Parker has to ask how to collect just enough without overheating. Its solar arrays are designed to retract as the spacecraft approaches the sun, leaving only a smaller portion exposed to the intense light. Those arrays are actively cooled, with water circulating through the system to carry heat away and radiate it into space. 1 gallon of water, doing its quiet little job aboard a spacecraft flying toward a star, is one of those details that makes space engineering feel oddly domestic. Somewhere inside this record-breaking solar mission is a cooling loop that, in spirit, is not so different from trying to keep a kettle from boiling over, although the kettle in this case is moving faster than anything humans have ever built. That speed is another part of Parker's character. The spacecraft does not merely drift close to the sun. It dives in along a highly stretched orbit, gathering speed as solar gravity pulls it inward, then swings back out again before repeating the journey. After several flybys of Venus, Parker reached a record approach of about 3.8 million miles from the sun's visible surface and a speed of about 430,000 miles per hour. NASA reported that during later close approaches, including one in December 2025, Parker again matched that record distance and speed while gathering data from inside the sun's atmosphere. It is difficult to make that speed feel real. 430,000 miles per hour is not a number that fits neatly into ordinary experience. A commercial airplane becomes a patient insect by comparison. A highway speed limit becomes almost philosophical. At such speeds, Parker could cross enormous distances in the time it takes someone on Earth to make tea and then forget where they put it. But speed alone is not the point. Parker is fast because it is falling deep into the sun's gravity well. The closer it gets, the faster it moves, and that fast motion is part of how it survives the most dangerous region. It does not linger near closest approach as if admiring the view. It sweeps through, gathers data, and continues along its path. That rhythm gives the spacecraft repeated chances to sample the near-Sun environment without spending the entire mission in the harshest conditions. The path that gets Parker there is not simple. You might imagine that going to the sun would be easy, because the sun's gravity is always pulling. Just aim inward and let nature handle the rest. Spaceflight, being fond of embarrassing intuition, disagrees. Earth is moving around the sun at high speed, and a spacecraft launched from Earth carries that sideways motion with it. To fall much closer to the sun, Parker has to reduce that orbital motion. That is where Venus comes in. The spacecraft uses repeated flybys of Venus as gravity assists, not mainly to gain speed in the usual outward mission sense, but to reshape and tighten its orbit so it can pass closer and closer to the sun. NASA describes the mission as using 7 Venus gravity assists over nearly 7 years to gradually shrink its orbit. This gives Parker's journey a patient quality, even though the spacecraft itself moves incredibly fast. It does not simply launch straight into its deepest solar dive. It loops, adjusts, returns, and gradually lowers its closest approach. Venus acts like a silent partner in the mission, not the destination, but the gravitational helper that makes the destination reachable. There is something elegant in that. To touch the sun, we first needed the help of another planet. Not with engines or machinery of its own, of course, but with gravity, timing, and the careful geometry of motion. A spacecraft built on Earth borrows a little orbital influence from Venus so that it can study the star that lights them both. Still, surviving the sun is not only about heat and trajectory, it is also about autonomy. When Parker is near the sun, Earth is far away in a practical sense. Radio signals take minutes to cross the distance, and the spacecraft cannot wait for a person in a control room to notice a problem, discuss it calmly, make a decision, send a command, and hope all is still well. If the heat shield is not aligned properly, the spacecraft must correct itself quickly. NASA has described sensors along the edge of the heat shield's shadow that can detect unwanted sunlight and alert the spacecraft so it can adjust its pointing and keep its instruments protected. This means Parker is not merely a remote-controlled object. It has to look after itself. It has onboard systems that monitor orientation, detect danger, and make corrections. In ordinary life, this might be compared to a person walking through strong rain, while keeping an umbrella angled against the wind. If the wind shifts, you do not phone someone across town and ask which way to tilt the umbrella. You move it immediately. Parker does the spacecraft version of that, except the rain is intense sunlight and radiation. The umbrella is a carbon composite heat shield, and the consequence of getting it wrong is not damp hair but mission-ending damage. The instruments behind that shield are the reason for all this effort. Parker is not simply trying to break records. It is not a stunt, though it certainly has the drama of one. Its purpose is to measure the sun's environment close to the source. NASA describes the spacecraft as carrying 4 instrument suites designed to study magnetic fields, plasma, energetic particles, and images of the solar wind. These instruments are meant to help answer long-standing questions about the corona, the acceleration of the solar wind, and the origins of high-energy solar particles. One instrument suite is called Fields, and its job is to measure electric and magnetic fields, waves, turbulence, shocks, and magnetic reconnection in the near-Sun environment. This is crucial because the corona and solar wind are not just hot gas drifting outward. They are plasma, a state of matter made of charged particles, and charged particles respond strongly to magnetic and electric fields. If you want to understand why the corona is so hot, why the solar wind speeds away, or why storms erupt, you have to understand the magnetic structure around the Sun. Fields is Parker's way of listening to invisible forces. It measures things that cannot be seen directly, but shape almost everything the plasma does. Another instrument suite is called Whisper, the wide-field imager for Parker Solar Probe. It is the mission's imaging instrument, and it looks at large-scale structures in the corona and solar wind before the spacecraft flies through them. That is a clever pairing. Whisper can see structures ahead, such as coronal mass ejections, jets, and other solar material moving outward, while other instruments later measure the particles and fields directly as those structures pass over the spacecraft. It is a bit like seeing clouds on the horizon, and then feeling the rain on your hand, except the clouds are made of plasma, and the rain is solar wind. Then there is the suite called SWEEP, short for solar wind electrons, alphas and protons. Its job is to count and characterize the most common particles in the solar wind. That includes electrons, protons and helium nuclei, often called alpha particles. Some of its sensors are tucked in safer regions, but one especially important instrument, the Solar Probe Cup, faces the Sun and sits outside the protection of the main heat shield, so it can directly catch the solar wind flowing outward. Because it has to endure sunlight that would destroy ordinary materials, parts of this exposed hardware are made from high-temperature alloys. NASA has noted that Parker's Field's antennas and Solar Probe Cup use niobium alloy materials to withstand the intense solar heat when they extend beyond the shield. That detail is one of the loveliest bits of mission design, because it shows that Parker cannot hide completely. To learn what it came to learn, some parts must peek out into the danger. Most of the spacecraft stays in the shadow, but a few instruments must meet the solar environment directly. There is no way to sample the solar wind properly if every sensor stays politely behind the curtain. The Solar Probe Cup is like a tiny scientific hand held out toward the Sun, not to touch a surface, but to catch the flow of particles streaming away from it. It is exposed because knowledge sometimes requires exposure. Carefully planned exposure, certainly. Highly engineered exposure, but exposure all the same. The fourth major science package studies energetic particles, the faster and more dangerous particles that can be accelerated by solar activity and travel through interplanetary space. These particles matter because they are part of the space weather story. They can affect spacecraft, astronauts, electronics, and radiation conditions beyond Earth's protective atmosphere. By measuring them close to where they are born or accelerated, Parker can help scientists understand how solar eruptions produce particle storms. Far from the Sun, many effects have already mixed together, like trying to understand a conversation after hearing only an echo down a hallway. Close to the Sun, the original event is fresher. The clues have not been blurred as much by distance. The spacecraft itself was designed, built, and is operated by the Johns Hopkins Applied Physics Laboratory for NASA. That matters not because a script should become a list of institutional credits, but because missions like this are not the work of one person with a wrench and a thrilling idea. They are the result of teams. Thermal engineers, physicists, instrument scientists, software developers, guidance specialists, material scientists, mission planners, technicians, launch teams, communications experts, and many others all contribute to making a small spacecraft behave intelligently in one of the harshest environments ever explored. Parker may be alone near the Sun, but it carries the work of a large human community with it. It also carries a name with history. Eugene Parker, the solar physicist for whom the mission is named, predicted the existence of the solar wind in the 1950s. His idea helped change how scientists understood the Sun's influence, showing that the star does not merely shine from a distance but continuously sends material outward through the solar system. The mission named for him was launched in 2018, and he lived to see the launch of the spacecraft bearing his name. NASA later noted that Parker pioneered modern understanding of the Sun, and that the spacecraft continues exploring questions connected to his work. There is something deeply satisfying about that. Science often moves slowly enough that the person who asks the question never sees the final instrument built to answer it. But here, the connection was unusually direct. A scientist proposed that the Sun drives a continual wind. Decades later, a spacecraft named Parker flew closer to the source of that wind than any spacecraft before it. That does not mean one person solved the Sun. Science does not usually work like that, and the Sun would be a rather large thing to solve before lunch. But it does mean that one idea helped open a path, and the spacecraft now travels that path in metal, carbon, sensors, and light. One of the surprising things about Parker is that the corona itself is not as deadly to the spacecraft as its temperature might suggest, at least not in the simple way we might imagine. The corona can reach millions of degrees, which sounds instantly fatal. But temperature and heat are not the same thing. Temperature describes how energetic the particles are. Heat transfer depends on how many particles are there and how much energy they actually deliver to an object. The corona is extremely thin, so even though its particles are very energetic, there are not many of them compared with something dense like boiling water or the air close to a flame. NASA uses this distinction to explain why the spacecraft can pass through such a hot region without simply melting. The greater heating problem for Parker is the direct sunlight striking the shield, which is why the reflective, insulating thermal protection system is so essential. That is a useful reminder that the Sun is not dangerous in only one simple way. It is not just hot like a stove. It is bright, magnetic, radiative, particle-rich, electrically active, and variable. Different parts of the spacecraft face different dangers. The shield deals with intense solar radiation. Materials outside the shield must tolerate high temperatures. Electronics must survive radiation. Communications must work across changing distances. The power system must gather energy without overheating. The guidance system must keep the shield aimed correctly. Each solution depends on every other solution. A spacecraft is not a pile of clever parts. It is a fragile agreement among systems, and near the Sun that agreement must be kept with extraordinary discipline. The mission plan also has to accept silence. During the closest parts of solar encounters, Parker cannot always send home a constant stream of reassuring messages. It may operate autonomously, gather data, and then later transmit information back to Earth when conditions and geometry allow. NASA reported that after its closest approaches, Parker checked in with flight controllers at the Johns Hopkins Applied Physics Laboratory by sending a beacon tone showing that its systems were operating normally. A beacon tone is not a dramatic message. It does not arrive with orchestral music. But for mission teams, it can be the most beautiful little sound in the solar system. It means the spacecraft survived. It means the shield held. It means the computers are awake. It means the instruments may have captured another priceless set of measurements from inside the atmosphere of a star. It is easy to imagine the spacecraft as brave, though of course bravery belongs to living things. Parker does not feel fear. It does not admire the view. It does not know that it is setting records or fulfilling a dream older than astronomy. But machines can still become carriers of human qualities because we build them for human purposes. Parker carries our curiosity into a place we cannot go. It holds its shield toward the sun because human engineers understood that it must. It measures fields and particles because human scientists knew what questions to ask. It loops past Venus because human mission designers found a path through celestial motion. It survives because thousands of small decisions were made correctly, tested carefully, and trusted at the edge of the possible. So when we meet Parker, we are not meeting a large spacecraft, we are meeting a specialist. A little probe with a very narrow job and a very harsh workplace. It is not built to land. It is not built to return samples. It is not built to carry people. It is built to enter the sun's environment, keep itself alive, and report what it finds. That makes it one of the most focused explorers ever launched. Some spacecraft wander among worlds. Some orbit planets for years. Some stare into deep space. Parker dives inward, again and again, toward the source of the solar wind and the mystery of the corona. And as it does, the old phrase from the beginning of our journey becomes less like a headline and more like an engineering achievement. Touching the sun required more than courage. It required knowing where to put the shield, how to cool the panels, how to measure invisible fields, how to keep instruments alive, how to borrow help from Venus, how to let a spacecraft make decisions when Earth is too far away to guide it moment by moment, and how to accept that a small machine can teach us about a star because it has been built with enough patience to survive one. The next step is to follow Parker across the boundary that made the mission famous, into the outer atmosphere where the sun no longer feels like a distant object, but like the environment itself, where the corona is not a pale glow seen during an eclipse, but a region of particles, waves, and magnetic fields pressing around the spacecraft as it passes through. By the time Parker's solar probe was ready to enter the sun's outer atmosphere, it had already done something that sounds a little backwards. It had travelled through space not to get away from the sun, but to fall closer to it. Most space stories point outward. They carry us toward Mars, Jupiter, Saturn, icy moons, distant comets, or the black edges of the solar system. Parker's path does the opposite. It loops inward again and again, giving up enough of its original motion around the sun to sink deeper into the star's domain. With every pass by Venus, its orbit becomes tighter. With every return toward the sun, the light grows harsher, the solar disk grows wider, and the spacecraft enters a region where the sun is no longer simply something ahead, it becomes the environment. This is an important shift because the sun does not have a surface in the way Earth has a surface. There is no solid ground beneath the glow. There is no place where the spacecraft could land, lower a ramp, and collect a small bag of solar dust with a little shovel. The sun is a vast sphere of hot plasma, and what we call its surface is really the visible layer from which most of the light we see escapes into space. That visible layer is called the photosphere. It is the part that gives the sun its familiar disk in the sky, though it should be said very clearly that familiar does not mean safe to look at directly. Above the photosphere is the chromosphere, a thinner and more irregular layer, and beyond that stretches the corona, the sun's outer atmosphere. The corona is the region Parker was built to enter. From Earth, it is usually hidden by the brightness of the solar surface. During a total solar eclipse, when the moon covers the bright disk of the sun, the corona appears as a faint pale glow around the black circle of the moon. It can look delicate from the ground, like a soft halo. But that gentle appearance is misleading. The corona is a place of extreme temperatures, magnetic loops, waves, charged particles, and flowing plasma. It is the region where some of the sun's deepest mysteries become visible, not because they are easy to see, but because they leave patterns in the motion of matter and fields. Crossing into the corona is not like crossing a border drawn on a map. There is no sign saying welcome to the solar atmosphere. Please keep your heat shield facing forward. The corona thins gradually as it extends outward, and its boundary is shaped by the sun's magnetic activity. Scientists use a particular physical boundary called the Alfvén critical surface to describe the place where the solar material effectively stops being tied closely to the sun and becomes the outward flowing solar wind. Inside this boundary, magnetic and plasma waves can still travel back toward the sun. Outside it, the solar wind is moving outward so strongly that disturbances can no longer easily move upstream toward the star. The material has broken free. That may sound subtle, but it is central to the meaning of touching the sun. The sun's atmosphere does not end at a hard edge. Instead, there is a transition between plasma that still belongs to the sun in a close magnetic sense, and plasma that has escaped into the solar system as solar wind. Parker touched the sun by crossing that transition and sampling the region inside it. It did not touch a glowing surface. It did something more scientifically useful. It entered the part of space where the sun's outer atmosphere still holds sway, and it measured particles and magnetic fields there directly. For decades, scientists had studied the corona from a distance. They had used eclipses, telescopes, satellites, and mathematical models. They had watched structures expand outward. They had measured the solar wind near Earth and from spacecraft throughout the solar system. They had built a picture of how solar material streams away from the star. But studying the solar wind near Earth is like studying smoke after it has drifted far downwind from a fire. You can learn a great deal, but the smoke has already spread, mixed, cooled, and changed. If you want to understand how it first rose, you need to go closer to the source. Parker was built to do that for the sun. The first confirmed passage into the corona happened during one of Parker's close solar encounters in 2021. The spacecraft crossed the Alfvén critical surface several times during that pass. That detail matters because it showed that the boundary is not smooth. It is not a perfect sphere surrounding the sun like a glass shell. It has folds, spikes, and valleys. Parker moved in and out of the corona because the boundary itself was uneven, shaped by magnetic structures and activity below. Imagine sailing near a coastline hidden by fog. From far away, you might draw the coast as a simple curve. Once you approach it, you discover bays, cliffs, inlets, and peninsulas. Parker found something similar, though the coastline was made not of rock and water, but of magnetic connection and escaping plasma. This changed the way scientists could think about the sun's outer atmosphere. Before Parker, the location of that critical boundary had to be estimated from models and indirect observations. Different conditions on the sun can move it inward or outward. Solar activity changes. Magnetic structures expand and contract. The corona is not a static object. Parker provided direct evidence by crossing the boundary itself, and the spacecraft's instruments could measure the changing conditions as it moved through different regions. It was no longer only a theoretical line, it was a physical transition that a spacecraft could experience. The word experience should be used carefully, of course. Parker does not feel anything. It does not notice the corona as a warmth on its skin or a pressure in its chest. But its instruments record changes. They measure the direction and strength of magnetic fields. They count particles. They detect waves and turbulence. They capture images of structures in the solar wind. In scientific terms, that is a kind of machine experience. It is the spacecraft's way of telling us what the environment is doing. When Parker crosses a boundary, it does not describe it in words. It returns data, and scientists translate that data into a clearer understanding of the star. Inside the corona, the spacecraft is moving through plasma. Plasma is often called the fourth state of matter, but that phrase can sound more mysterious than it needs to. In ordinary gas, atoms and molecules move freely but remain mostly neutral. In plasma, enough energy has been added that electrons are separated from atoms, creating a mixture of charged particles. Because the particles are charged, they respond strongly to magnetic and electric fields. This makes plasma complicated in a very active way. It can flow, twist, carry currents, generate waves, and organize itself along magnetic field lines. The corona is not simply hot gas. It is a magnetic plasma environment, and that is why it can behave in ways that seem unfamiliar from everyday life. One of the strange things about the corona is that it is extremely hot but very thin. This can seem confusing at first. If someone says a region is millions of degrees, it sounds as though anything entering it should instantly vaporize. But temperature is not the same as the amount of heat delivered to an object. The particles in the corona are moving with very high energies, but there are relatively few of them compared with the dense air around us, or the liquid water in a pot. A person could not survive there, to be absolutely clear, and neither could ordinary equipment, but the spacecraft's main heating challenge comes from intense sunlight, striking its shield rather than from dense hot material pressing against it. This is why the heat shield and the spacecraft's orientation are so important. Parker survives not because the corona is gentle, but because the mission understands which dangers matter most and how to manage them. As Parker moves through the corona, it also moves through the birthplace of the solar wind. The solar wind is a continuous flow of charged particles streaming away from the sun. It fills interplanetary space and creates the heliosphere, the vast bubble of solar influence surrounding the planets. Near Earth, the solar wind has already travelled a long way. By the time it arrives here, it has interacted with magnetic structures, waves, and material spread across space. Parker measures it much closer to where it begins, before all those later changes have fully blurred the original conditions. That is why crossing the corona is so valuable. It brings the spacecraft into the region where the wind is still being shaped. For scientists, the key question is not just that the solar wind exists, but how it is accelerated. Something drives particles outward from the sun and helps them reach high speeds. The sun's heat contributes, but the full story involves magnetic fields, waves, and complex plasma processes. Parker can measure fluctuations in the magnetic field and the motion of particles close to the sun, giving researchers clues about how energy is transferred through the corona and into the escaping wind. It is a little like standing close enough to a river's source to see which springs feed it, rather than measuring the river far downstream and trying to reconstruct every bend from memory. During its early encounters, Parker also detected sudden bends in the magnetic field known as switchbacks. These are sharp changes where the magnetic field briefly folds back on itself. Before Parker, scientists had seen hints of these structures farther from the sun, but the spacecraft found them in great numbers close to the sun. Switchbacks became one of the mission's most discussed discoveries because they may be connected to how energy and motion move through the corona and how the solar wind is accelerated. They are not little decorative wiggles in the data. They are signs that the magnetic environment near the sun is dynamic and full of unexpected structure. As Parker got closer, it began to show that some switchbacks are connected with features lower in the solar atmosphere, especially near regions where magnetic fields open outward. These open magnetic field regions can act like channels along which solar material escapes into space. This is important because the solar wind is not uniform. It comes in faster and slower streams, and those streams can originate from different types of solar regions. By linking measurements close to the sun with visible and magnetic features on the solar surface, researchers can begin to connect the wind measured by Parker with the places where it begins. That connection is one of the mission's central achievements. It ties the flowing material in space back to structures on the star itself. There is also the matter of streamers. During eclipses, the corona often appears with long, bright structures extending outward. These streamers are shaped by magnetic fields and dense coronal material. Parker has flown through features associated with streamers, giving scientists direct measurements of regions that had long been seen from afar. Again, this is the difference between looking at a cloud and flying through it with instruments. From a distance, the streamer is a shape. Up close, it becomes a physical environment with particles, fields, motions, and boundaries. The corona is full of such structures because the Sun's magnetic field is complicated. The Sun rotates, but not like a solid ball. Different latitudes rotate at different rates. Hot plasma rises and falls inside it. Magnetic field lines become twisted, stretched, and rearranged. Sometimes magnetic energy is released suddenly, producing flares or helping launch coronal mass ejections. The corona is where many of these magnetic structures become visible, arching outward in loops or opening into space. Parker does not see the entire system at once, but it passes through pieces of it, measuring the local conditions in enough detail to help scientists connect small-scale processes with large-scale solar behavior. Crossing the corona also helps scientists test their models. Modern solar physics depends heavily on computer simulations, because the Sun is too large, too hot, and too complex to reproduce fully in a laboratory. These simulations use physical principles to predict how plasma and magnetic fields should behave, but a model must be checked against reality. Before Parker, some regions close to the Sun could only be inferred. Now scientists can compare predictions with direct measurements. If the data agrees with the model, confidence grows. If it does not, the model must improve. That is not a failure. That is science doing what it is supposed to do, gently but firmly reminding everyone that the universe gets the final edit. The moment of entering the corona was also a psychological milestone for space exploration. For years, mission planners and scientists had described Parker as a spacecraft that would touch the Sun. When the data confirmed that it had crossed into the corona, the phrase became more than a promise. It became a completed act. Humanity had sent a machine into the atmosphere of a star. That statement is true, but it should not be rushed past. A species that once used shadows to estimate the time of day had built a spacecraft capable of sampling the magnetic environment of the Sun from within. The distance between those two achievements is not just technological, it is cultural. It is the long accumulation of observation, mathematics, engineering, and curiosity. Still, the crossing was not a single dramatic doorway after which everything became simple. Parker continues to make repeated close passes, and each pass can sample different solar conditions. The Sun changes over its activity cycle, and Parker's measurements become especially valuable as solar activity rises and different structures appear. One pass might carry the spacecraft through a quieter region. Another might bring it near more disturbed fields or through material shaped by recent eruptions. Over time, the mission builds a fuller picture, not a snapshot but a sequence. The Sun is not a still object, so understanding it requires repeated visits. The spacecraft's orbit makes those visits brief and intense. At closest approach, Parker is moving extremely fast. It does not hover in the corona. It sweeps through, protected by its shield, instruments running, systems watching their own health, solar panels trimmed for survival, antennas not always pointed conveniently toward Earth. Later, when the geometry allows, data is sent home. Scientists then work through the measurements, comparing the timing, particle counts, field directions, waves, and images. The dramatic part happens near the Sun, but the understanding happens slowly on Earth in analysis, discussion, and careful checking. This is a useful contrast. Public imagination likes the single moment, the crossing, the record, the phrase touched the Sun. Science needs those moments too, but it also needs the quiet month afterward, when researchers ask exactly what the instruments recorded and what it means. A boundary crossing can become a headline in a day, but the details can take years to fully understand. Parker's measurements are not just souvenirs from a daring journey. They are pieces of a very large puzzle involving plasma physics, magnetic fields, solar activity, and the way our star influences the space around every planet. The invisible border into the corona therefore matters for several reasons at once. It marks a new kind of exploration. It gives direct access to the region where the solar wind is being formed. It helps test ideas about magnetic fields and plasma waves. It reveals that the sun's atmospheric boundary is structured rather than smooth. It lets scientists connect faraway observations with local measurements. And it reminds us that the sun is not a simple glowing ball, but a layered, changing, magnetically active star with an atmosphere that reaches outward into space. For someone on Earth, all of this may still feel remote. The corona is not part of daily weather reports. No one wakes up and says the outer solar atmosphere looks a little unsettled this morning, unless they happen to work in heliophysics, in which case they very well might. But the corona is where many space weather conditions begin. The solar wind comes from the sun. Solar eruptions move through the corona. Energetic particles can be accelerated in solar events. By understanding the region close to the source, scientists can improve the chain of knowledge that connects solar activity to effects near Earth. Better understanding can eventually mean better warnings, better models, and better protection for satellites, communications, navigation systems, astronauts, and power infrastructure. The crossing also changes the way the sun feels in the imagination. It is still distant, still huge, still dangerous, still impossible for humans to visit in person. But it is no longer only an object watched from afar. A human-made instrument has entered its atmosphere and returned information. That does not make the sun smaller. If anything, it makes the sun more impressive, because proximity reveals complexity. From Earth, the sun can look like a plain bright disk. Up close, it becomes a structured magnetic world of waves, streams, folds, and boundaries. The closer Parker gets, the less simple the sun becomes. There is a quiet lesson in that. Many things seem simple at a distance. A star becomes a dot. A storm becomes a cloud shape on the horizon. A forest becomes a green patch from a hill. But closeness adds detail, and detail adds understanding. Parker crossed into the corona not to make the sun less mysterious, but to make the mystery more specific. Instead of asking only why the corona is hot, scientists can ask which waves carry energy, where magnetic structures change direction, how particles gain speed, where switchbacks form, and how the boundary of the corona shifts with solar activity. Better questions are often a sign of progress. As Parker continues its path, the corona is no longer just the faint crown seen during an eclipse. It is a place the spacecraft can sample. It is a region with measurable conditions. It is the starting ground for the solar wind and a key to the sun's influence across the solar system. The invisible border has been crossed, but crossing it does not end the story. It opens the next problem, the old and stubborn question that made scientists want to go there in the first place. Once inside the corona, once surrounded by the sun's outer atmosphere, Parker can begin helping us understand why this thin crown above the visible surface becomes so intensely hot, and how energy climbs outward through a star in a way that still challenges ordinary expectation. At first glance, the sun seems as though it ought to be easy to understand in one basic way. The deeper you go toward the glowing centre, the hotter things should become. The farther you move away from that centre, the cooler things should get. That is how ordinary experience trains us to think. Stand close to a fire and your face gets warm. Step back and the heat fades. Put your hand near a lamp and you feel more warmth than you do from across the room. Heat in daily life appears to weaken with distance. So when scientists began studying the sun carefully, it would have been reasonable to expect the same pattern. The visible surface should be very hot, the layers above it should be somewhat cooler, and the outer atmosphere should be cooler still. A neat arrangement, a tidy arrangement, the kind of arrangement that would make a physics teacher slightly happier and a student's notes easier to read. But the sun, being the sun, declined to be tidy. The visible surface of the sun, the photosphere, is indeed hot. It is hot enough to glow with a bright light that fills our daytime sky. It is hot enough that the word surface can be misleading, because this is not a solid shell, but a layer of dense, glowing plasma from which much of the sun's visible light escapes. Yet above that layer, in the corona, the temperature rises enormously. The corona can reach millions of degrees, far hotter than the photosphere below it. That is the great solar mystery that has bothered scientists for generations. The sun's outer crown is hotter than the bright layer beneath it. It is as if you walked away from a fireplace and found the far wall of the room blazing hotter than the flames themselves, which would be inconvenient for home decoration and extremely confusing for anyone trying to make soup. The corona is not easy to see from Earth with ordinary eyes. Most of the time, the photosphere is so bright that it overwhelms the faint outer atmosphere completely. During a total solar eclipse, when the moon covers the bright disk of the sun, the corona appears as a soft pale glow extending outward. It looks delicate and almost calm, like a white crown around darkness. That appearance can be deceptive. The corona is not a quiet halo. It is a restless region of plasma shaped by magnetic fields, waves, loops, eruptions, and streams of particles escaping into space. It is thin compared with the layers below, but the particles inside it can carry extremely high energies. This is where the problem begins. The corona is thin, distant from the denser surface, and yet somehow heated to extraordinary temperatures. One of the first things to understand is that temperature in the corona does not mean quite what our bodies imagine when they hear the word hot. If you placed an ordinary object in dense boiling water, heat would move into that object quickly, because there are many water molecules colliding with it. In the corona, the particles are much more spread out. They are moving with very high energy, but there are fewer of them. So the corona has a very high temperature, while its thinness changes how heat is delivered. This is one reason Parker Solar Probe can pass through the corona without simply vanishing in a puff of science fiction smoke. The spacecraft still needs serious protection from intense sunlight and radiation, but the thinness of the corona matters. Temperature and heat transfer are related, but they are not the same thing. That small distinction saves many explanations from becoming deeply misleading. Still, the mystery remains. Even if the corona is thin, its particles are extremely energetic. Something must be giving them that energy. Something must be carrying energy upward from lower layers of the sun and depositing it in the outer atmosphere. The question is not whether the corona is hot. The question is how it gets that way and how it stays that way. For a long time, scientists have suspected that the answer lies in the sun's magnetic field. The sun is not simply a glowing ball of hot material. It is a magnetic star. Its plasma conducts electricity, and moving charged particles create and respond to magnetic fields. These fields are dragged, twisted, tangled, stretched, and rearranged by the motion of plasma inside and on the surface of the sun. The result is a magnetic environment far more complicated than anything we usually encounter on Earth, unless one counts the mysterious behavior of headphone cables in a pocket. Magnetic fields can store energy. That is one of the key ideas. The visible surface of the sun is constantly churning. Hot plasma rises, cools, sinks, and moves in vast patterns of convection. These motions jostle the magnetic field lines rooted in the solar surface. Imagine tying long elastic cords to a moving floor and then slowly twisting, pulling, and braiding them. Energy builds in the distorted cords. In the sun, magnetic fields can become stressed by the continual movement of plasma below. When these fields rearrange, energy can be released into the corona. This release can heat particles, launch waves, and accelerate material outward. The details are complicated, but the broad idea is simple enough. The lower sun moves. The magnetic field is forced to move with it. Energy is stored. Then some of that energy is released above the surface. One proposed mechanism is magnetic reconnection. This happens when magnetic field lines change their arrangement and release stored energy. In the corona, magnetic fields can be twisted into complex shapes. When they reconnect, energy that had been locked in the magnetic structure can be converted into heat, motion, and particle acceleration. Large reconnection events can produce solar flares, releasing enormous amounts of energy. But scientists also think that much smaller reconnection events may happen constantly throughout the corona. These tiny bursts are sometimes called nanoflares, not because they are small in any ordinary human sense, but because they are small compared with the larger solar flares. The idea is that many small energy releases, happening again and again across the corona, could add up to enough heating to maintain the corona's extreme temperature. This is an attractive idea because the sun's surface is full of magnetic complexity. Small loops, bright points, active regions, and shifting patterns appear all the time. If the corona is being heated by countless small magnetic rearrangements, then the heating might be widespread and continuous, rather than dependent only on rare giant explosions. That would help explain why the corona remains hot even when the sun is not producing a major flare. It's a bit like warming a house not with one enormous bonfire in the living room, which would be dramatic and not recommended, but with many tiny heaters distributed everywhere. Each little event may not seem enough by itself, but together they could matter. Another major idea involves waves. The sun's surface is constantly moving, and those motions can send waves upward along magnetic field lines into the corona. One important type of wave in plasma is often called an Alfvén wave, named after the physicist Hannes Alfvén. These waves travel through magnetized plasma, carrying energy. If such waves move upward from the lower layers of the sun and then dissipate in the corona, they could heat the particles there. The challenge is to understand how much energy the waves carry, where they travel, and how efficiently they deposit that energy as heat. A wave that simply passes through the corona without losing energy would not solve the problem. The energy has to be transferred into the plasma. The wave idea is appealing because the sun naturally produces motion. The surface churns, shakes, and shifts. Magnetic field lines can act like guides for waves, carrying disturbances upward. But the corona is not a clean, simple laboratory. It is turbulent, structured, and constantly changing. Waves can reflect, interact, break apart, and feed turbulence. Turbulence can then create smaller and smaller motions, passing energy down to tiny scales where it can finally heat particles. This kind of process is familiar in a broad sense from fluids on Earth. Stir cream into tea, and you see swirling motion break into smaller swirls. Stir the atmosphere and weather becomes complex. In the corona, the fluid is plasma, the stirring is magnetic and convective, and the result may be one of the main routes by which the outer atmosphere becomes hot. For many years, the difficulty was not a lack of ideas, it was a lack of direct measurements close enough to the region where the heating and acceleration occur. Scientists could observe the corona from far away, they could study light emitted by hot plasma. They could measure the solar wind when it reached spacecraft farther from the sun. They could run simulations and compare them with observations. But the key region close to the sun remained hard to sample directly. It is one thing to hear a strange sound from another room and guess what instrument is playing. It is another to walk into the room and find the orchestra. This is where Parker Solar Probe becomes so important. By flying into the corona and making measurements close to the sun, Parker can test these heating ideas in the environment where they matter most. It measures magnetic fields, electric fields, waves, plasma particles, and energetic particles. It can detect turbulence close to the sun before it has evolved over long distances. It can measure sudden changes in magnetic direction. It can sample the young solar wind before it has fully spread through interplanetary space. These measurements help scientists decide which processes are carrying energy, where that energy is going, and how the corona and solar wind are connected. One of Parker's surprising early findings was the abundance of sharp magnetic field bends called switchbacks. These are sudden reversals or kinks in the magnetic field, where the field briefly folds back on itself before returning to its usual direction. Farther from the Sun, spacecraft had seen hints of such structures, but Parker found them close to the Sun in large numbers. This was important because it showed that the near-Sun environment is more dynamic and structured than expected. Switchbacks may be connected to waves, turbulence, or magnetic structures rooted near the solar surface. They may also play a role in transferring energy and momentum into the solar wind. Scientists are still working through exactly how they form and what role they play. But Parker showed that they are not rare curiosities. They are part of the near-Sun story. Parker has also helped link some solar wind features to magnetic funnels near the surface. In certain regions, magnetic field lines open outward into space rather than closing back down in loops. These open regions can become channels through which solar material escapes. If switchbacks and bursts of fast wind are related to these open magnetic structures, then scientists can begin connecting what Parker measures in space to specific features on the Sun itself. That is a major step. It turns the problem from a vague question about general heating into a more precise question about where energy is released and how that energy travels. The corona heating problem and the solar wind problem are closely related. The corona is hot, and from that hot corona the solar wind escapes. Understanding one helps with the other. If magnetic waves or reconnection heat the corona, they may also help push particles outward. If turbulence transfers energy through this plasma, it may both heat particles and contribute to the wind's acceleration. The Sun is not running separate departments, one labelled heating and another labelled wind. The same magnetic processes may be involved in both. That is why Parker's measurements are so valuable. It samples the region where the corona is heated and where the solar wind is still young. There is also an interesting timing issue. The corona cannot be explained only by asking what the average temperature is. Scientists want to know how heating changes from place to place and moment to moment. Active regions above sunspots may behave differently from quieter regions. Open magnetic field lines may behave differently from closed loops. Solar activity rises and falls across the solar cycle. Parker's repeated passes through different solar conditions allow researchers to build a more complete picture. One encounter cannot explain the whole corona any more than one afternoon can explain Earth's entire climate. The Sun has patterns, moods, and cycles. Studying it requires returning again and again. The mystery is also a reminder that common sense is built for human-sized environments. Our instincts about heat come from fires, stoves, sunlight on skin, warm rooms, cold windows, and hot drinks. They are useful instincts for living on Earth, but the corona is a magnetized plasma around a star. Energy can be carried by waves along magnetic fields. Particles can be accelerated by reconnection. Turbulence can move energy between scales. Thin plasma can have a high temperature without behaving like dense hot air. In that environment, the idea that farther means cooler is too simple. The Sun teaches us that heat is not only a matter of distance, it is a matter of transport, storage, release, and interaction. Even the word crown used for the corona can be slightly misleading. A crown sounds like something placed on top of the Sun, a decorative outer layer. In reality, the corona is physically connected to the layers below and to the solar wind beyond. Magnetic fields thread through it. Particles pass through it. Eruptions begin within it, or move through it. The corona is not an ornament. It is an active transition region between the Sun and the space environment that surrounds the planets. The mystery of why it is so hot is not a narrow curiosity. It affects how we understand the entire flow of energy from the Sun into the solar system. For life on Earth, the corona's heat may sound distant, but it is part of the chain that leads to space weather. A hot, dynamic corona helps drive the solar wind. Magnetic energy in the corona can be released in flares and eruptions. Coronal mass ejections can travel outward and, if aimed toward Earth, disturb our magnetic environment. The better scientists understand the corona, the better they can understand the origins of events that may affect satellites, communications, navigation, and power systems. This is not the kind of weather that tells you whether to bring an umbrella. It is the kind that tells engineers and operators whether sensitive technology may need extra attention. Parker's work, therefore, connects a deep physics puzzle with practical concerns on Earth. There is something satisfying about the way Parker approaches the problem. It does not solve the corona by looking for one magical answer. It gathers evidence in a place no spacecraft had measured before. The answer may involve several processes working together. Waves may carry energy upward, turbulence may help dissipate it. Magnetic reconnection may release energy in bursts both large and small. Different regions may be heated in different ways. The corona may not have one simple heater hidden behind the curtain. It may be warmed by a combination of restless magnetic activity, continual motion, and plasma physics operating across many scales. That is less tidy than a single explanation, but the sun has never promised tidiness. Imagine for a moment the view from Parker's instruments, not visually in the human sense, but scientifically. The spacecraft is behind its heat shield, moving faster than any human-made object before it, surrounded by the sun's outer atmosphere. Its sensors detect fields that twist and shift. Particle instruments count streams of electrons, protons, and helium nuclei. Wave instruments record fluctuations moving through the plasma. The imager sees structures flowing outward before the spacecraft encounters them directly. Each measurement is a small report from the corona. Not a story in words yet, but a set of clues. Later, back on Earth, those clues are compared with models, checked against other observatories, and slowly turned into understanding. That slow turning is important. The public phrase "NASA touched the sun" is wonderfully simple. The scientific result is more detailed. Parker did not touch the corona and instantly solve every solar mystery. It crossed a boundary and began collecting the kind of data needed to reduce uncertainty. It showed that the near-sun environment contains abundant switchbacks. It sampled the corona directly. It measured the young solar wind. It gave scientists a closer look at fields, waves, and particles in the region where heating and acceleration are happening. These are not small achievements. But the corona heating problem is deep, and science advances by narrowing the unknown, not by waving politely at it and declaring victory before supper. The mystery also has a pleasing historical shape. For centuries, humans saw the corona only during eclipses. It appeared briefly, and then sunlight returned and hid it again. Astronomers chased eclipses across continents to capture a few minutes of data. Then space telescopes allowed longer and clearer observations. Now Parker flies through the region itself. The same faint crown that once appeared only when the moon covered the sun has become a place a spacecraft can enter. The question has changed from what is that glow to what processes heat this plasma and launch this wind. That change is the story of solar science growing more intimate with its subject. And still, the basic surprise remains easy to state. The outer atmosphere is hotter than the visible surface. You do not need advanced mathematics to feel the strangeness of that. It is one of those scientific puzzles that begins with a simple violation of expectation and leads into a complex world of magnetic fields, plasma waves, reconnection, turbulence, and space weather. Those are the best kinds of mysteries for a calm evening, really. They begin with something anyone can understand, and then quietly open into the machinery of a star. As Parker continues to make close passes, scientists will keep asking how energy moves from the lower sun into the corona. They will study whether waves carry enough energy. They will examine whether small reconnection events happen often enough. They will track how switchbacks form and evolve. They will compare open magnetic regions with closed loops. They will use Parker's measurements alongside solar telescopes that watch the whole sun from farther away. No single instrument can see everything. Parker is close and direct. Telescopes are broader and more continuous. Together they allow scientists to connect the small local details to the large visible structures. So the hot crown of the sun remains a mystery, but it is no longer a distant mystery in quite the same way. Parker has moved the question closer. It has brought sensors into the region where the heating happens. It has turned the corona from an unreachable glow into a measurable environment. The sun's outer atmosphere is still not fully explained, but the old puzzle now has new evidence pressing against it from inside the corona itself. And as that evidence builds, the next part of the story begins to move outward. Because the corona does not simply sit above the sun, hot and strange, keeping its secrets to itself. It expands, it releases particles, it feeds a continuous flow that streams past planets and fills the solar system. The same region that raises the question of coronal heat also gives birth to the solar wind, and Parker is close enough to watch that wind near the place where it first breaks free. The corona does not end politely. It does not form a neat outer wall around the sun and then stop, as if the star had decided that was quite enough atmosphere for one day. Instead, the corona expands outward. Its particles are heated, stirred, guided by magnetic fields, and finally released into space. From that release comes one of the most important and invisible features of our solar system, the solar wind. It is not wind in the way we feel wind on Earth. There are no breezes carrying the smell of rain, no gusts rattling windows, no leaves rolling down the pavement like they have somewhere important to be. The solar wind is a stream of charged particles, mainly protons and electrons with a smaller amount of helium nuclei and other ions, flowing outward from the sun in every direction. It is thin, fast, electrically active, and always there, filling the space between planets. If the sunlight we see is the sun speaking to our eyes, then the solar wind is the sun reaching out with matter. It is the star not merely shining, but shedding a continuous flow into the solar system. Earth, Mars, Venus, Jupiter, Saturn, comets, asteroids, spacecraft and dust grains all move through this outflow. The planets are not sitting in empty darkness, separated by perfect stillness. They are immersed in a restless solar atmosphere that has stretched far beyond the sun itself. In a very real physical sense, the sun does not stop at the bright disk we see in the sky. Its influence pours outward, carried by magnetized plasma, until it meets the pressure of material from interstellar space far beyond the planets. That huge region shaped by the solar wind is called the heliosphere. It is the bubble of solar influence around our planetary system. Inside it, the sun is the main source of the charged particles and magnetic fields that fill space. Outside it lies the wider environment between stars. The existence of this bubble tells us something simple but profound. The sun is not just a central lamp. It is an active body that creates the local space environment. The planets orbit inside the sun's breath, if we use the word gently and scientifically enough. The solar wind is that breath made measurable. For a long time, scientists did not know it was there. From Earth, space seems empty, because it is mostly empty compared with air, water, rock, or even the best attempt at cleaning beneath a sofa. But mostly empty is not completely empty. The idea that the sun continuously releases particles into space was developed by Eugene Parker in the middle of the 20th century. His work suggested that the corona was so hot that it could not simply sit still above the sun. It would expand outward, forming a wind that travels through the solar system. At first, this was not an obvious idea. A steady wind from the sun sounded bold, but spacecraft later confirmed it. Instruments beyond Earth detected streams of charged particles moving outward, and the solar wind became a central part of solar physics. This is one reason it feels so fitting that Parker Solar Probe carries Eugene Parker's name. The spacecraft named after the scientist who predicted the solar wind now flies into the region where that wind is being born. That is not just a tribute, it is a continuation of the question. Parker the physicist showed that the wind should exist. Parker the spacecraft asks how the wind begins, how it is accelerated, why it changes, and how its magnetic structure develops near the sun before it spreads across millions of miles. The solar wind has two broad personalities, though the real situation is much more complicated. There is fast solar wind and slow solar wind. Fast solar wind tends to come from regions where magnetic field lines open outward into space, often associated with coronal holes. These are not holes in the sense of gaps punched through the sun, but darker regions seen in certain wavelengths, where the corona is less dense and where magnetic fields are open enough to allow plasma to escape more freely. Slow solar wind is more variable and more difficult to pin down. It may come from boundaries between open and closed magnetic regions, from the edges of streamers, or from places where magnetic fields are rearranging and releasing material. Scientists have studied these differences for decades, but the exact birthplaces and acceleration processes have remained difficult to understand from far away. This is where Parker's closeness matters. By the time the solar wind reaches Earth, it has travelled a long distance. It has expanded, cooled, mixed with other streams, interacted with waves and turbulence, and carried with it a magnetic field that has been wound into a spiral shape by the rotation of the sun. Measuring the wind near Earth is valuable, but it is a little like tasting soup after it has been simmering for hours and trying to work out precisely when each ingredient was added. Near the sun, the ingredients are fresher. Parker can sample the wind before it has had as much time to evolve. It can measure the particles and magnetic fields close enough to preserve clues about their origin. The spacecraft does not ride the solar wind in the way a boat rides a river. It is not being swept helplessly outward from the sun. Parker follows its own orbit, falling inward and then swinging back out, crossing through regions where the wind is forming and flowing. But the phrase riding the solar wind captures something useful. The spacecraft moves through a current of charged particles, and its instruments are built to feel that current. They count particles, measure their speeds and directions, study their temperatures, and track the magnetic field embedded within the flow. From these measurements, scientists can reconstruct how the wind behaves near its source. One of the most important instruments for this work is the Solar Probe Cup. It is an exposed instrument that looks toward the sun and directly samples particles streaming outward. Most of Parker hides behind its heat shield, but this instrument must face the flow. It is built from materials that can survive extreme sunlight and heat because it cannot do its job from the safety of the shadow. This is one of the mission's quietly brave design choices. To understand the solar wind, Parker has to extend a sensor into it, the spacecraft equivalent of holding out a hand in a gale, except the gale is made of charged particles escaping a star, and the hand is a carefully engineered scientific cup that would not look especially impressive on a kitchen shelf, but is very impressive near the sun. As Parker passes through the near-sun environment, it finds that the solar wind is not smooth. That is one of the repeated lessons of this mission. From far away, it might be tempting to imagine the wind as a steady outward breeze, perhaps faster in some places and slower in others, but basically simple. Close up, it is full of structure. The magnetic field bends and twists. Particles arrive in bursts, waves travel through the plasma, streams vary from moment to moment. The young solar wind is not a calm flow leaving the sun like water from a garden hose. It is more like a complicated mountain river near its source, full of sudden channels, rocks, swirls, and hidden turbulence. One of Parker's most striking discoveries has been the abundance of magnetic switchbacks. These are sharp bends in the magnetic field, where the field briefly changes direction, sometimes so strongly that it seems to fold back on itself. Imagine walking along a path that generally leads away from a house, but every so often the path doubles back for a short distance before turning outward again. The overall route still leads away, but the local direction suddenly reverses. In the solar wind, these switchbacks are not footpaths, of course. They are changes in the magnetic field carried by the plasma. Parker found them close to the sun in surprising numbers, showing that the young solar wind is full of sudden magnetic folds. Switchbacks matter because they may carry information about how the solar wind is accelerated. They may be created by waves travelling outward from the sun. They may form when magnetic structures reconnect near the surface. They may be linked to jets of material emerging from open magnetic field regions. Scientists are still working to understand their origin, but Parker's close measurements have made the question much more concrete. Before, researchers could ask whether such structures existed close to the Sun. Now they can study them directly. They can ask where they appear, how common they are, how they change with distance, and whether they are connected to particular features in the lower atmosphere. The solar wind also carries the Sun's magnetic field outward. Because the Sun rotates, this magnetic field does not extend straight out like simple spokes on a wheel. It becomes wound into a spiral through space, sometimes called the Parker spiral, another connection to Eugene Parker's work. Near the Sun, the field is closer to its source and less stretched by distance. Farther out, the rotation of the Sun and the outward motion of the wind create a spiral pattern that reaches across the solar system. This magnetic field is important because charged particles move along and respond to it. It shapes the path of energetic particles, influences space weather, and helps define the structure of the heliosphere. The solar wind is not only a flow of particles, it is a carrier of energy, momentum, and magnetic information. It connects the Sun to the planets. When it reaches Earth, it encounters our planet's magnetic field. Most of the time, Earth's magnetic field deflects and guides the incoming solar wind around the planet, forming a protective region called the magnetosphere. But the interaction is not perfectly quiet. Energy from the solar wind can enter Earth's magnetic environment, especially when the orientation of the solar magnetic field allows stronger coupling. That energy can drive auroras, disturb satellites, affect radio systems, and contribute to geomagnetic storms. The story of space weather begins near the Sun, but its effects can reach right down into the routines of modern technology. This is why studying the solar wind at its birthplace matters. Space weather forecasting depends on understanding what leaves the Sun and how it changes on the way to Earth. If scientists can better understand how fast and slow wind streams form, how magnetic structures develop, and how energetic particles are accelerated, they can improve models of what may happen later. A forecast is only as good as the physics behind it. The more accurately researchers can describe the early solar wind, the better they can predict how disturbances might travel through space. It is useful to compare this with weather on Earth. If you want to predict a storm, you do not only look at the sky above your house, you study pressure systems, temperature, humidity, winds, ocean conditions, and how these features evolve over time. Space weather is similar in spirit but very different in substance. Instead of air, clouds, and rain, scientists track plasma, magnetic fields, radiation, and charged particles. Instead of weather stations across continents, they use spacecraft, solar telescopes, and models. Parker adds a new kind of weather station, one placed close to the source of the whole system. The solar wind also helps explain why comets have tails. When a comet approaches the Sun, solar heating causes gas and dust to escape from its icy nucleus. The solar wind and solar radiation then push this material away, forming tails that generally point away from the Sun. One tail is made of dust, and another is made of ionized gas shaped strongly by the solar wind and magnetic field. In this way, comets become visible traces of the Sun's outward influence. Long before spacecraft measured the solar wind directly, comet tails hinted that something from the Sun was sweeping outward through space. They were like weather vanes in the solar system, pointing away from the star. Near Earth, the solar wind is often invisible, but we see its effects in auroras. When charged particles and energy enter Earth's magnetic environment, some particles are guided toward the polar regions, where they collide with atoms and molecules high in the atmosphere. These collisions produce glowing curtains of light, green, red, purple, and sometimes faintly shimmering white. Auroras are beautiful, but they are also signs of a physical connection between Earth and the Sun. They are the atmosphere lighting up under the influence of solar particles and magnetic energy. A quiet green curtain over a snowy landscape may have begun as a disturbance in the solar wind days earlier. Parker's work brings the origin of that connection closer. This spacecraft samples the particles before they become distant solar wind, before they cross the orbit of Mercury, before they travel outward toward Earth and beyond. It measures conditions in the region where the corona opens into space. That helps scientists understand not only the wind itself, but also the way the Sun loses material and angular momentum over time. Stars like the Sun gradually lose mass through stellar winds. Over vast timescales, such winds also influence how stars rotate and evolve. So the solar wind is not merely a local inconvenience for satellites, it is part of the life of a star. The wind also comes from a surface that is not really a surface. This can be a little tricky, because we naturally imagine particles leaving from a visible edge. But the solar wind forms through the extended corona, and along magnetic structures that reach outward. There is no simple place where the wind begins in the way a river begins from one spring. Instead, different streams may originate from different magnetic regions, heights, and processes. Some flow along open field lines from coronal holes. Others may be released from closed magnetic regions when reconnection opens a path. Parker's mission helps sort out these origins by combining direct measurements with images and observations from other solar missions. This collaboration between spacecraft is important. Parker is close, but because it is close, it sees only the region around its path. Other observatories watch the broader Sun, tracking active regions, coronal holes, streamers, flares, and eruptions. When scientists combine Parker's local measurements with wider solar images, they can link what the spacecraft feels to what the Sun was doing at the time. It is like having one person inside a storm with sensitive instruments, while another watches the whole weather system from above. Neither view is complete alone. Together, they become much more powerful. One of the questions Parker helps answer is how the solar wind becomes turbulent. Turbulence is a word that makes airplane passengers grip armrests, but in physics it describes complex, chaotic motion across many scales. The solar wind is turbulent as it travels through space. Magnetic and velocity fluctuations interact, energy cascades from larger structures to smaller ones, and particles can be heated along the way. Close to the Sun, Parker can measure turbulence near its origin. This is important because turbulence may help heat the corona and accelerate the wind. It may also shape how energetic particles move through space. Again, the same processes are linked. Heating, acceleration, turbulence, and magnetic structure are not separate stories neatly filed in different cabinets. They are different parts of one active plasma system. The spacecraft's closeness also lets scientists study dust near the Sun. Tiny dust grains move through the inner solar system, and near the Sun some of them can be heated, altered, or destroyed. Parker has detected impacts from dust grains, and has helped study the dust environment close to the Sun. This may sound like a side note, but dust is part of the space environment. It affects spacecraft, reflects sunlight, and helps scientists understand the materials spread through the inner solar system. Even near a star, the small things matter. Space is full of tiny details that refuse to remain tiny once you start measuring them carefully. When Parker rides through the solar wind, it is also travelling through a region that is constantly changing because the Sun itself changes. The Sun follows an activity cycle of about 11 years, moving between quieter and more active periods. During active times, sunspots are more common, flares and eruptions occur more often, and the magnetic field becomes more complex. During quieter times, the large-scale structure of the wind can be more orderly, though never perfectly simple. Parker's mission spans changing solar conditions, giving researchers a chance to see how the near-Sun wind behaves across different phases of activity. That variation matters because space weather is strongest and most complicated when the Sun is active. There is a calm way to think about all of this. Even though the processes themselves are energetic, the Sun is constantly letting go of material. A tiny fraction of its plasma escapes outward, not enough to change the Sun quickly, but enough to fill the solar system with a thin, moving atmosphere. Parker moves through that atmosphere near its source. It listens to the magnetic field. It counts the particles, it watches structures pass, it samples the wind while it is still young, while it still carries the freshest signs of the corona below it. The spacecraft is not simply proving that the wind exists. That was already known. It is learning how the wind becomes itself. And that is a very different kind of knowledge. Knowing that a river exists is one thing. Knowing where it rises, why some channels run faster than others, how rocks shape the flow, where turbulence begins and how a flood forms is another. The solar wind is the river of the sun, though thinner, stranger and threaded with magnetic fields. Parker is travelling close to the headwaters. It does not stay there long. It sweeps through at enormous speed, protected by its heat shield, then carries its data outward and eventually sends it home. Each pass gives scientists another stretch of the river to study. The more we learn, the more the solar wind becomes not just a background flow, but a key to the sun's relationship with everything around it. It shapes planetary magnetic environments. It strips atmospheres from worlds that lack strong protection. Mars, for example, lost much of its ancient atmosphere over time, and interactions with the solar wind played an important role in that loss. Venus too interacts directly with the solar wind because it has no Earth, like global magnetic field. Comets grow tails under its influence. Giant planets form huge magnetospheres inside it. Spacecraft must be designed with it in mind. Astronauts beyond Earth's protective shield must be protected from the more dangerous particle events associated with solar activity. The solar wind is not a narrow stream passing through empty space. It is part of the operating environment of the solar system. Parker's journey into the young wind also helps connect the everyday sun with the extreme sun. Most days the solar wind flows steadily enough that we notice nothing at ground level, but sometimes the sun produces eruptions that disturb the flow dramatically. A coronal mass ejection can send a vast cloud of magnetized plasma outward. A flare can produce intense radiation. Energetic particles can be accelerated to high speeds. These events travel through and interact with the background solar wind. To understand the storm, scientists must also understand the medium through which the storm moves. The ordinary wind sets the stage for extraordinary events. So riding the solar wind from its birthplace is not just about following a stream of particles. It is about understanding the sun as an active source of space weather. It is about seeing how quiet flows and violent eruptions belong to the same magnetic system. It is about learning why some streams are fast, why others are slow, why the magnetic field folds into switchbacks, and how energy travels outward from the corona. It is about turning a once invisible idea into a measured physical environment. For all its speed and engineering, Parker's work has a surprisingly patient quality. The spacecraft does not answer everything in a single pass. It returns again and again, each time sampling a different slice of the solar environment. Scientists build the picture gradually, comparing encounters, connecting measurements to solar regions, checking theories, improving models. The solar wind is continuous, but our understanding of it arrives in pieces. A field change here, a particle burst there, a switchback, a wave, a stream, a magnetic connection to a coronal hole. Piece by piece the wind becomes less mysterious, and as that picture sharpens, the next question naturally grows from it. If the sun constantly sends out this wind, what happens when the flow is disturbed by something much larger and more violent? What happens when magnetic energy erupts, when radiation bursts outward, when a cloud of plasma leaves the corona and begins travelling across space toward Earth? The solar wind is the steady background, the stars' continual outflow, but the sun also has storms, and those storms can turn the invisible connection between sun and Earth into something powerful enough to trouble the technologies we depend on every day. The solar wind is always flowing, but the sun is not always calm. Most of the time, its outward stream of charged particles moves through the solar system like a steady background current, changing from fast to slow, thick to thin, smooth to turbulent, but still part of the normal breathing of a star. Then there are the moments when the sun becomes more forceful. Magnetic fields twist too tightly. Energy builds in the corona. Plasma structures rise and stretch. A region that looked stable from a distance suddenly rearranges itself, and the sun releases a storm into space. These storms are not storms in the earthly sense. There are no clouds in the ordinary way, no rain, no thunder rolling over rooftops, no one standing at a window wondering whether the washing should have been brought in earlier. Solar storms are made from radiation, magnetic fields, and charged particles. They are born in the sun's atmosphere and travel outward through interplanetary space. They can arrive at Earth days later, or in some cases affect our environment almost immediately through radiation moving at the speed of light. They are invisible to our eyes until Earth's upper atmosphere responds with auroras, those glowing curtains of light that can make the night sky look as if it has quietly learned to breathe. The beginning of a solar storm is usually magnetic. The sun's magnetic field is not smooth and simple. It is dragged around by the motion of plasma below the surface. It loops out of the photosphere, arches through the corona, tangles, stretches, and sometimes stores enormous energy. Sunspots are one visible sign of this magnetic activity. They appear darker because they are cooler than their surroundings, but they're still intensely hot by ordinary standards. Around sunspots, magnetic fields can be especially strong and complicated. Active regions like these are often where flares and eruptions begin. A solar flare is a sudden burst of radiation caused by the rapid release of magnetic energy in the sun's atmosphere. It can brighten across many wavelengths, from radio waves to X-rays. The energy travels outward at the speed of light, which means the effects of the radiation can reach Earth in about 8 minutes, the same time sunlight takes to cross the space between us. That is very fast by human standards, and rather rude from the point of view of warning systems. When a strong flare occurs on the side of the sun facing Earth, its radiation can disturb the upper atmosphere almost immediately. This can affect high-frequency radio communication, especially on the sunlit side of the planet. For people on the ground, this usually passes unnoticed. For aviation, ships, emergency communication, and certain radio users, it can matter. But flares are only part of the story. Sometimes the sun releases something much larger and heavier, a coronal mass ejection. This is a vast eruption of magnetized plasma from the corona. A coronal mass ejection can carry billions of tons of solar material into space. It expands as it travels, pushing through the solar wind like a huge moving cloud. The word cloud sounds soft, perhaps too soft, as though one might see a pleasant white shape drifting above a summer field. A coronal mass ejection is not that kind of cloud. It is a moving structure of charged particles and magnetic fields, capable of disturbing planetary environments across enormous distances. Not every flare produces a coronal mass ejection, and not every coronal mass ejection is associated with a major flare. They are related parts of solar activity, but the sun does not always pair them neatly for our convenience. Sometimes a flare releases radiation without launching a major plasma cloud. Sometimes an eruption sends out a coronal mass ejection with only a modest flare. Scientists watch both because they affect Earth in different ways and on different timescales. Radiation from flares arrives quickly. A coronal mass ejection takes longer, often 1 to several days depending on its speed and the path it follows. That delay gives forecasters time to watch, model, and prepare, though the details remain challenging. A third part of solar storm activity involves solar energetic particles. These are high-speed charged particles, often accelerated by flares, shock waves driven by coronal mass ejections, or other magnetic processes near the sun. They can travel through space along magnetic field lines and reach spacecraft and planetary environments. For satellites, astronauts, and instruments beyond Earth's protective atmosphere, these particles can be hazardous. They can damage electronics, increase radiation exposure, and interfere with detectors. Earth's atmosphere and magnetic field protect people at ground level very well, which is a comforting thing to remember. But outside that protection, solar energetic particles become a serious part of mission planning. The journey from the Sun to Earth is not a straight empty road. The space between the planets is filled with solar wind, and embedded within that wind is the Sun's magnetic field. Because the Sun rotates while the wind flows outward, the magnetic field forms a spiral through space. Any eruption leaving the Sun must travel through this moving, structured environment. It may speed through faster wind or slow wind. It may drive a shock wave ahead of itself. It may interact with streams released earlier. Its magnetic field may rotate or become distorted as it expands. By the time it reaches Earth, it may not have the same shape it had when it left the corona. This is one reason space weather forecasting is difficult. Scientists can observe a coronal mass ejection as it leaves the Sun, estimate its speed and direction, and model its journey. But a small difference in the eruption's path can determine whether Earth receives a direct hit, a glancing blow, or nothing significant at all. Even when a solar storm does reach Earth, its effects depend strongly on the orientation of its magnetic field. If the magnetic field carried by the incoming storm is aligned in a way that connects efficiently with Earth's magnetic field, energy can enter Earth's magnetosphere more easily. If the orientation is less favourable, the storm may pass with weaker effects. This magnetic detail is crucial, but it can be hard to measure far in advance. Earth is not defenceless. Our planet has a magnetic field generated deep inside by the motion of liquid iron alloys in the outer core. This field extends into space and forms the magnetosphere, a protective bubble around Earth. When the solar wind reaches this bubble, it is mostly deflected around it. The side facing the Sun is compressed. The night side stretches out into a long magnetotail. Under normal conditions, this system quietly manages the constant solar wind. It is one of the reasons Earth is such a comfortable place for life at the surface. Without the magnetic field and atmosphere, our relationship with the Sun would be much harsher. During a geomagnetic storm, however, the magnetosphere becomes disturbed. Energy from the solar wind or an incoming coronal mass ejection enters the system. The magnetotail can store and release energy. Electric currents intensify in near-Earth space and in the upper atmosphere. Charged particles are guided down toward polar regions, where they collide with atoms and molecules high above the ground. Those collisions produce auroras. Oxygen can glow green or red. Nitrogen can add purples and blues. The result is one of the most beautiful visible signs of solar activity. A storm that began in twisted magnetic fields on the Sun becomes shifting light over Earth's polar skies. Auroras can be gentle, but the storm behind them may have practical consequences. Modern civilization uses technologies that are sensitive to space weather. Satellites orbit above much of the atmosphere, where they're exposed to charged particles and radiation. A strong solar storm can increase drag on satellites in low Earth orbit by heating and expanding the upper atmosphere. This can alter satellite orbits and require extra corrections. Energetic particles can damage electronic components, degrade solar panels, or cause errors in onboard systems. Operators may put satellites into safer modes during severe events, reducing risk but also interrupting service. Navigation systems can also be affected. Signals from global navigation satellites pass through the ionosphere, a region of Earth's upper atmosphere filled with charged particles. Solar storms can disturb the ionosphere, making signals slower, scattered, or less reliable. This can reduce the accuracy of positioning systems. Most of the time, the effects are manageable, but for aviation, maritime navigation, surveying, agriculture, emergency response, and many other fields, accurate timing and positioning matter. A disturbance that begins as magnetic energy on the Sun can end as a navigation error on Earth. It is a long chain, but a real one. Radio communication is another part of the story. High-frequency radio signals can bounce off the ionosphere, allowing communication over long distances. When solar radiation changes the ionosphere, those radio paths can be disrupted. Polar routes are especially vulnerable because energetic particles and magnetic disturbances often enter near the poles. Airlines that fly over polar regions may need to adjust routes during strong space weather events to maintain communication and reduce radiation exposure. Again, most people on the ground may notice nothing. The sky looks normal. The weather at street level is unchanged. But high above, in the layers where radio waves travel and aircraft cross remote routes, the sun's activity can matter. Power grids can also be affected by severe geomagnetic storms. Changing magnetic fields around Earth can induce electric currents in long conductors, including power lines. These geomagnetically induced currents can stress transformers and other grid equipment. The danger is usually associated with very strong storms, but the consequences could be serious. In 1989, a geomagnetic storm contributed to a major power blackout in Quebec. In 1859, the famous Carrington event produced extraordinary auroras and disrupted telegraph systems. Telegraph operators reported sparks and shocks, and some systems continued sending messages even after being disconnected from their normal power sources because currents had been induced by the storm. The world of 1859 was far less electrically dependent than ours. A similar event today would raise much more complex concerns. This does not mean we should imagine every solar flare as a disaster waiting at the door. Most solar activity is modest. Earth is struck by solar wind every day and continues quite happily, with breakfast still occurring, birds still making unreasonable amounts of noise, and people still losing their keys at the usual rate. Space weather is a risk to understand, not a reason to panic. The sun has always been active. What has changed is our dependence on technologies that stretch into space, rely on precise timing, and use long electrical networks. We have become more connected, and therefore more sensitive to disturbances in the space environment. That is why missions like Parker Solar Probe matter. To forecast storms well, scientists need to understand how they form near the sun. It is not enough to see a coronal mass ejection after it has already erupted. Researchers want to know what magnetic conditions lead to eruptions, how energy builds in active regions, how particles become accelerated, and how structures in the corona shape the storm's early motion. Parker cannot watch the whole sun at once, but it can measure the near-sun plasma and magnetic environment directly. Combined with observations from solar telescopes and other spacecraft, its data helps improve the physical models used to understand space weather. Parker's location close to the sun gives it access to the early stages of the solar wind and to conditions in the corona that influence how storms travel. A coronal mass ejection does not move through an empty vacuum. It moves through the background solar wind, and that wind can speed it, slow it, compress it, or shape it. If scientists understand the background wind better, they can improve predictions of how eruptions will move. Parker's measurements of turbulence, magnetic switchbacks, particle flows, and coronal structure all contribute to this. The ordinary wind and the storm are connected. The calm background sets the road. The eruption is the vehicle racing along it. Other spacecraft also play important roles. Observatories near Earth watch the sun in many wavelengths. Spacecraft positioned between Earth and the sun can measure incoming solar wind before it reaches us, giving a short warning of conditions just upstream from Earth. Missions viewing the sun from different angles help track eruptions as they expand. Together they form a network of observers. Parker adds the close-up view near the source. It is like studying hurricanes with satellites, ocean buoys, aircraft and ground stations, except the hurricane begins on a star, and the aircraft is replaced by a heat-shielded probe moving through plasma at record speed. The science of space weather also depends on timing. Solar radiation from a flare arrives almost at once. In practical terms, energetic particles may arrive within minutes to hours. Coronal mass ejections usually take longer. This creates different warning challenges. Some effects must be detected and responded to quickly. Others can be modelled over a day or more. Forecasters look for signs of active regions on the sun, monitor flare activity, track eruptions, measure solar wind conditions, and update predictions as new data arrives. It is a field that blends astronomy, plasma physics, engineering, and practical risk management. The Sun becomes not only an object of wonder, but also a source of operational information. There is a strange intimacy in that. A magnetic structure on the Sun, larger than Earth, can release a burst of energy. A wave of radiation crosses space. A cloud of plasma expands outward. Instruments detect it. Scientists issue alerts. Satellite operators adjust systems. Power grid managers watch for currents. Airlines consider communications and routes. Aurora watchers check forecasts and step outside under dark skies. The chain stretches from the corona to control rooms, from solar magnetic fields to human decisions. The Sun is not simply far away. It participates in our technological lives. Parker helps us understand this participation at its origin. When it flies close to the Sun, it can sample conditions that are otherwise hidden by distance. It can move through the young solar wind before it has become the mature flow measured near Earth. It can detect the magnetic complexity that shapes particle motion. It can observe structures that may later affect the space environment farther out. Its measurements are not space weather forecasts by themselves, but they improve the foundation on which better forecasts can be built. A good forecast begins with good physics, and good physics begins with good measurements. Solar storms also remind us that the Sun is a star, not a machine built for our convenience. It does not turn itself down because satellites are expensive. It does not avoid releasing eruptions toward Earth because someone is trying to use navigation in a city with too many one-way streets. It follows its own magnetic cycles and plasma processes. Our task is not to control it. Our task is to understand it well enough to live with it intelligently. That is a mature kind of exploration, not the fantasy of conquering nature, but the practical wisdom of learning its habits. The beauty of this story is that the same events that can threaten technology can also produce some of the most memorable sights in the sky. Auroras are space weather made visible. They are the soft public face of a vast magnetic interaction. People travel to see them, stand in the cold to photograph them, and speak about them with a kind of quiet awe. Yet behind the colours is a chain of charged particles, magnetic fields, and solar activity. Science does not make auroras less beautiful by explaining them. It gives the beauty a longer journey. The light above the horizon began as energy in the Sun's atmosphere, travelled across space, entered Earth's magnetic environment, and finally met the gases of our upper air. As we follow solar storms from the Sun to Earth, we begin to see the solar system less as a set of isolated worlds and more as a connected environment. The Sun sends out wind. Planets carve out magnetic cavities or stand exposed. Storms travel through the shared space between them. Earth's atmosphere glows. Satellites adjust. Power systems prepare. Mars, lacking a strong global magnetic shield like Earth's, interacts with the solar wind in a different and more exposed way. Jupiter, with its enormous magnetic field, creates a vast magnetosphere of its own. Every world meets the Sun differently, but every world is touched by it. This connected view is one of the reasons heliophysics is so important. It studies not only the Sun, but the Sun as the creator of a space environment. Parker Solar Probe, by flying close to the star, helps fill in the missing inner part of that environment. It gives scientists information from the region where storms and wind are young. It helps link the magnetic behaviour of the corona to the conditions that eventually spread through the solar system. The journey of a solar storm is not just a dramatic episode, it is a test of our understanding of the whole Sun-Earth system, and as Parker continues to gather data, the practical hope is that one day space weather warnings will become more accurate, more detailed, and more useful. We may better predict which eruptions will matter, when they will arrive, how strong their magnetic impact may be, and what technologies are most at risk. We may learn how to protect satellites more effectively, plan astronaut missions more safely, and design power systems with greater resilience. That future depends on many missions and many models, not Parker alone. But Parker is giving us something that was missing for a long time: measurements close to the source. The storms from the sun are powerful, but they are not random magic. They are physical events with causes, structures, and pathways. Magnetic fields store energy. Reconnection releases it. Plasma erupts. Particles accelerate. The solar wind carries disturbances outward. Earth's magnetic field responds. Technology sometimes feels the disturbance. The night sky sometimes lights up. Step by step, the chain can be studied, and the closer we study it to the beginning, the better we can understand what arrives at the end. So the sun storms are not separate from the gentle sunlight of an ordinary morning. They belong to the same star. The same magnetic activity that makes the corona dynamic also launches eruptions. The same solar wind that flows quietly past Earth can become disturbed by a powerful ejection. The same protective magnetic field that keeps our planet safe can turn storm energy into auroras. Parker's mission brings us closer to the origin of all these processes, not only so we can admire the sun's power, but so we can prepare for it. And after following the storms outward, after seeing how solar activity can travel from the corona to the edge of Earth's magnetic shield, the story turns back toward the spacecraft itself and the measurements it has actually returned. Parker was not sent merely to survive, or merely to cross a symbolic boundary. It was sent to find things, to reveal what the near-sun environment is truly like, and to show scientists details that had been hidden by distance for as long as humans had been watching the daylight sky. By the time Parker's solar probe began sending home measurements from inside the sun's outer atmosphere, scientists already knew they were not receiving ordinary travel notes. This was not a postcard from a quiet place. It was data gathered inside a region of plasma, magnetic fields, waves, dust, particles, and violent sunlight, close enough to the source that many of the usual smooth descriptions of the solar wind began to break apart. From near Earth, the sun's outflow can seem comparatively steady, a broad stream of charged particles moving past our planet after travelling a very long way. Close to the sun, Parker found something much more restless. The solar wind was not a simple breeze leaving a star. It was patchy, impulsive, folded, structured, and full of motion that distant spacecraft had been too far away to see clearly. NASA described Parker's early measurements as revealing a complicated and active solar wind system that is not visible from Earth. That may sound like a modest statement, but it changes the feeling of the whole sun. For many years, scientists measured the solar wind after it had already travelled across tens of millions of miles of space. By then, many of the fine details had been stretched, mixed, and blurred. Parker moved inward to catch the wind while it was still young, before it had settled into the more familiar flow measured near Earth. The difference is a little like listening to a piece of music through a wall, and then finally stepping into the room where the instruments are playing. The melody was always real, but the texture becomes different. You hear the small interruptions, the quick changes, the scrape of a bow, the intake of breath, the parts that distance had politely hidden. One of the first surprises Parker found was a strange kind of magnetic folding called a switchback. These are sudden bends in the magnetic field carried by the solar wind. For a brief time, the field can whip back on itself, so that instead of pointing generally away from the sun, it appears to turn sharply and point back toward it. The particles are still part of the outward solar wind, but the magnetic structure has made a sudden zigzag. Spacecraft had seen hints of these features before, but Parker found them close to the sun in numbers that made them impossible to dismiss as rare oddities. NASA reported that Parker saw quick reversals in magnetic fields, sudden faster-moving jets of material, and clusters of switchbacks during its first close encounters. This was not just a curious wrinkle in the data. Switchbacks became one of Parker's most important clues, because they may be connected to how the solar wind gains speed and how energy moves through the corona. A switchback is not a little visual kink that scientists can admire, and then file away under strange but harmless. It is a sign that the near-Sun magnetic environment is far more dynamic than a smooth outward flow. If the magnetic field is folding, snapping, waving, or being shaped by motions near the surface, then the young solar wind is carrying a memory of those processes. Parker found that memory while it was still fresh. The next question was where these switchbacks come from. Were they born near the solar surface, where magnetic fields emerge from the churning plasma below? Or were they formed higher up in the corona as the solar wind moved outward? Parker helped narrow this down. As the spacecraft moved closer to the Sun, its data showed that some switchbacks occur in patches and align with magnetic funnels emerging from the photosphere, the Sun's visible layer, between large convection patterns called supergranules. NASA reported that these findings pinpointed one source region of switchbacks near the solar surface and suggested that magnetic funnels may also be linked to the origin of part of the fast solar wind. That discovery gives the solar wind a more specific birthplace. Instead of imagining the wind simply leaking from the Sun in all directions, scientists can start connecting streams of particles to particular magnetic structures. Some regions of the Sun have magnetic field lines that loop back down, trapping plasma in arches. Other regions have field lines that open outward, giving material a path into space. Magnetic funnels may act like escape routes, guiding particles from the lower solar atmosphere into the expanding wind. Parker does not see every funnel everywhere, but it gives scientists direct measurements close enough to connect the wind to its roots. This matters because the solar wind has different forms. Fast solar wind and slow solar wind do not behave in exactly the same way, and they may not come from exactly the same places. Parker's data has strengthened the idea that fast solar wind is partly powered by switchbacks connected to magnetic structures near the Sun, but the slow solar wind remains more difficult. NASA reported in 2025 that Parker confirmed two types of slow solar wind, one with small-scale switchbacks and one without those magnetic variations, while scientists are still working to confirm their exact origins. That kind of answer may seem incomplete, but it is actually the honest shape of progress. Parker did not fly into the corona and return with one neat sentence that solved the Sun before bedtime. It returned with better evidence, sharper questions, and fewer places for uncertainty to hide. The slow solar wind is dense, variable, and important for space weather because it can interact with fast streams and create disturbed conditions near Earth. Learning that slow wind has different types is a significant step, even if the final origin story is still being written. Science often advances not by making everything simpler, but by making the categories more accurate. Parker also found that the boundary of the corona is not smooth. This was one of the most important parts of the mission's famous first contact with the Sun. The spacecraft crossed the Alphen critical surface, the boundary where solar material breaks free enough to become the solar wind. Before Parker, scientists had estimated where this boundary might be, but they did not know its detailed shape. When Parker crossed it, the spacecraft passed in and out of the corona several times. That meant the boundary was wrinkled with spikes and valleys rather than a clean spherical shell. NASA reported that this finding showed the edge of the solar atmosphere is more complex than previously thought. There is a wonderfully physical quality to that result. A boundary that might look smooth in a diagram turns out, when touched, to have texture. It is not a perfect line. It moves with the Sun's activity. It bulges outward in some places and draws inward in others. It is shaped by magnetic fields and plasma conditions below. Parker did not merely cross a border. It discovered that the border has weather of its own. That makes sense once we remember that the corona is not a still atmosphere. It is a changing magnetic environment, expanding, folding, and releasing material outward. Inside the corona, Parker also flew through structures that had usually been seen only from far away. During one encounter, the spacecraft passed near coronal streamers and through a region called a pseudostreamer. These are large structures rising above the Sun's surface, often visible during total solar eclipses. From Earth, they appear as parts of the faint corona, pale rays or extensions around the darkened moon. Parker's close passage gave scientists a very different perspective. NASA described the spacecraft flying through coronal structures that can be observed during an eclipse, with conditions inside one pseudo-streamer becoming quieter, particles slowing, and switchbacks dropping. That quiet region is especially interesting because it shows that the corona is not uniformly chaotic. Even close to the Sun, there are different neighbourhoods. Some are full of rapid changes and magnetic folds. Others are calmer, more ordered, or dominated by stronger magnetic structures. To understand the Sun, scientists have to map those differences. The corona is not one simple layer with one simple behaviour. It is a landscape of plasma conditions, except the landscape is made from fields, particles, and flows rather than hills and rivers. Parker passes through that landscape quickly, but its instruments can still feel the changes. The spacecraft's images added another layer to the discoveries. Parker's wide field imager for solar probe, known as WHISPER, looks sideways from behind the heat shield and images structures in the corona and solar wind. On its record close pass in late 2024, Parker captured the closest ever images to the Sun, from about 3.8 million miles above the solar surface. NASA reported that these images showed the corona and solar wind shortly after the wind was released, including the heliospheric current sheet, where the Sun's magnetic field changes direction, and the collision of multiple coronal mass ejections in high resolution. That is a remarkable thing to picture gently. The spacecraft is not staring directly into the Sun like someone making a very poor decision on a bright afternoon. It is protected by its heat shield, while its imager looks outward at the material flowing through the corona. In those images, scientists can see structures in the solar wind racing away from the Sun. They can see eruptions piling into one another. They can watch the geometry of space weather near its birthplace. This is not only beautiful, it is useful. When coronal mass ejections collide or merge, their paths can change, their magnetic fields can mix, and their effects can become hard to predict. Seeing those interactions close to the Sun helps scientists understand how solar storms develop before they reach Earth. Parker also changed what scientists know about dust near the Sun. Space is not perfectly clean. Tiny dust grains from comets and asteroids drift through the inner solar system, scattering sunlight and forming a faint glow called the zodiacal light. For decades, scientists predicted that close enough to the Sun, dust should thin out or disappear because the intense heat would vaporize it. Parker found evidence that dust does indeed begin to thin close to the Sun, supporting the idea of a dust-free zone near the star. NASA reported that Parker's WHISPER instrument saw this thinning, giving the first direct signs of a long-predicted region where dust is depleted by solar radiation. This is one of those discoveries that feels quieter than switchbacks or solar storms, but it is still elegant. The spacecraft was sent mainly to understand the corona and solar wind, yet as it flew close to the Sun, it also helped reveal what happens to dust in extreme sunlight. A star does not only shape plasma, it also shapes the smallest solid particles drifting near it. Near the Sun, even dust has a life story, and that story may end in vapor. Parker's instruments also found that small energetic particle events are more common near the Sun than scientists expected, even during quieter solar conditions. These particles matter because energetic particles from the Sun can be hazardous to spacecraft and astronauts. Far from the Sun, by the time the particles reach Earth or other spacecraft, they may have lost some of the clues about how they were accelerated. Close to the source, Parker can measure them when their history is less blurred. NASA reported that Parker observed many more tiny energetic particle events than expected, helping scientists study their sources, acceleration, and transport. That finding reminds us that the Sun is active even when it seems quiet. Solar minimum does not mean nothing is happening. It means the Sun is less active compared with its stormier phases, but magnetic processes continue. particles still accelerate, and the solar wind still flows. Parker's closeness reveals small events that would be difficult or impossible to identify from farther away. This is another form of the same lesson. Distance smooths the sun, closeness complicates it. One of Parker's early surprises involved rotation in the solar wind. Scientists expected that the solar wind would carry some rotational motion as it left the sun, because the sun itself rotates, and its magnetic field is anchored in solar material. But Parker found stronger sideways motion than expected closer to the sun. That matters because the way the solar wind carries angular momentum away from the sun affects how the sun evolves over long timescales. It is a technical detail with a large consequence. A star loses not only particles but also rotational influence through its wind. Parker's close measurements help refine how that process works. The overall picture Parker has returned is of a corona and young, solar wind that are far more structured than the older wind measured near Earth. Near our planet, the solar wind can seem like an established current. Near the sun, Parker sees bursts, folds, streams, jets, patches, streamers, dust changes, particle events, and magnetic boundaries. This does not mean earlier measurements were wrong. They were measuring the wind after a long journey. Parker is measuring a younger version of the same system, before the delicate features have been washed together by distance. That difference is essential for understanding space weather. By the time a solar disturbance reaches Earth, it is already the result of many processes. It may have begun as a magnetic eruption in the corona. It may have moved through fast or slow solar wind. It may have collided with other eruptions. Its magnetic field may have rotated or mixed. Its particles may have been accelerated by shocks. If scientists only study the final arrival near Earth, they're trying to reconstruct the whole story from the last page. Parker gives them earlier pages, and those earlier pages are messy in the best scientific way. They show that switchbacks are common. They show that some switchbacks connect to magnetic funnels near the visible solar surface. They show that the coronal boundary is uneven. They show that the solar wind close to the sun is not a smooth flow, but an active, changing system. They show that slow wind has multiple forms. They show coronal mass ejections interacting in high resolution near the sun. They show dust thinning close to the star. They show small energetic particle events that were more numerous than expected. None of these is the final answer to the sun. Together they are a new kind of closeness. It is worth remembering how extraordinary that closeness is. Parker is not gathering this information from a comfortable orbit around Earth. It is flying through the sun's outer atmosphere, protected by a heat shield, moving at record speeds, often out of contact during the most intense parts of its passes, then sending data home after it survives. The measurements arrive as numbers, fields, particle counts, images, timing, and instrument records. Scientists then translate them into physical meaning. A jagged magnetic trace becomes a switchback. A change in particle speed becomes evidence of a different solar wind stream. A dimming dust signal becomes a clue to a dust-depleted zone. A set of images becomes a record of eruptions merging in the corona. There is no single photograph that can contain what Parker found. Its discoveries are distributed across measurements. Some are visual, some are invisible, some are local, felt only as the spacecraft passes through a region. Some require careful comparison with solar images from other missions. This is why the mission is so powerful. It does not only give us a closer view, it gives us a closer physical encounter. The spacecraft measures the environment from within it, which is different from watching it from outside. The sun that emerges from Parker's findings is not simply a hot ball with a bright face. It is a magnetic engine. It is a source of winds and storms. It has a corona whose boundary is wrinkled. It has magnetic funnels that may feed the fast solar wind. It has slow wind with more than one identity. It has switchbacks like sudden folds in the path of invisible fields. It has eruptions that can collide and merge close to the star. It has dust near it thinning under fierce radiation. It has energetic particle events happening even when the sun appears comparatively quiet. The simple daytime disk has become, through Parker's measurements, a living physics laboratory, though not living in the biological sense, and certainly not a laboratory with sensible working temperatures. These findings also change how we imagine the phrase touch the sun. It was never only about crossing a distance. The true achievement is that Parker touched the sun and found texture. It found that the atmosphere has structure. It found that the wind is born with complexity. It found that magnetic fields can fold back on themselves. It found that some boundaries are uneven and some quiet places exist inside stormy regions. It found that the sun's influence does not begin as a smooth river, but as a restless branching magnetic outflow. And the story is still moving. Parker continues to return data from close solar passes, and each pass adds another piece to the picture. Some discoveries will be refined, some interpretations may change, some mysteries will divide into smaller mysteries, as they tend to do when scientists look closely. That is not disappointing. That is the sign of a mission doing real work. The sun is not yielding a single secret. It is revealing an environment. As we move toward the final part of this journey, the meaning of Parker's findings begins to settle into something practical as well as wondrous. Every switchback, every streamer, every measurement of the young solar wind, every image of eruptions merging near the sun helps scientists understand the chain between solar activity and Earth. The spacecraft's discoveries are not only about a distant star, they are about the space weather that can affect satellites, navigation, radio communication, astronauts, and power grids. Parker went close to the sun not merely to say that we had reached it, but to help us learn how to live under it with a little more wisdom. Touching the sun may sound like the end of a story, the grand final moment when humanity reaches out across space and finally brushes the atmosphere of its own star. But in many ways, it is the beginning of a more practical story. It is the beginning of learning how to live more wisely with the sun, not just admire it, not just depend on it, but understand its moods well enough to protect the delicate technology that now surrounds our world. Parker Solar Probe was not sent into the corona simply because it would make a good headline, though admittedly it does make a very good headline. It was sent there because the sun is not only a source of light and warmth, it is also the source of space weather, and space weather can reach into modern life in ways that are quiet, invisible, and occasionally rather inconvenient. Most of the time, sunlight feels simple. It comes through a window, it warms a wall, it makes dust visible in the air, which is charming until you remember someone has to clean it. We feel the sun as weather, seasons, warmth, and daylight. But beyond that familiar sunlight, the sun is constantly releasing charged particles, magnetic fields, radiation, and sometimes enormous eruptions that travel outward through the solar system. These processes create an environment that Earth moves through every day. NASA describes Parker Solar Probe as collecting measurements and images in the corona to improve understanding of the origin and evolution of the solar wind, while also making critical contributions to forecasting space environment changes that affect life and technology on Earth. That last idea is the key. Parker is not only helping scientists answer old questions about the corona, it is helping build the knowledge needed for better warnings. A solar storm does not announce itself by knocking politely on the magnetosphere and saying it will arrive after lunch. It begins as physical processes in the sun's atmosphere. Magnetic fields twist and reconnect, plasma erupts, particles accelerate, radiation spreads. A coronal mass ejection may expand outward like a huge magnetic cloud. If Earth happens to be in the path, that solar disturbance can interact with our planet's magnetic field and upper atmosphere. Most people at ground level may notice nothing at all, perhaps only a bright aurora if they are lucky and standing somewhere dark. But the technology above us and around us may notice very much indeed. Satellites are among the first concerns. They orbit in a region where Earth's atmosphere is thin or nearly absent, and where protection from space weather is much weaker than at the surface. A strong solar storm can disturb satellite electronics, increase radiation exposure, and heat Earth's upper atmosphere so that it expands slightly outward. For low Earth orbit satellites, that expansion can create more drag. Drag is small, but in orbital mechanics, small effects can become very important if you happen to be a spacecraft trying to remain in the right place. NASA notes that space weather can alter satellite orbits, shorten satellite lifetimes, or interfere with onboard electronics. This means a storm that begins in the corona can eventually matter to communications, navigation, weather monitoring, Earth observation, and the many quiet services that depend on spacecraft behaving properly. Then there is navigation. We have become used to little blue dots on maps telling us where we are, even when we ourselves are not entirely sure. Navigation systems depend on signals travelling from satellites to receivers on Earth. Those signals pass through the ionosphere, the charged upper layer of our atmosphere. During geomagnetic storms, the ionosphere can become disturbed and the signals can be delayed, scattered, or distorted. NOAA's Space Weather Prediction Center explains that geomagnetic storms can modify signals from radio navigation systems such as GPS and GNSS, degrading accuracy. For everyday walking directions, this may be mildly annoying. For aviation, shipping, farming equipment, surveying, emergency response, and systems that rely on precise timing, it becomes more serious. The sun, in other words, can make your map less certain without ever appearing cloudy. Radio communication is also vulnerable. Solar flares can produce strong X-rays that affect the upper atmosphere and degrade or block high-frequency radio communication, especially on the sunlit side of Earth. NOAA describes these events as radio blackout storms, and also notes that energetic particles can interfere with radio communications at high latitudes during solar radiation storms. This is especially relevant for aircraft flying polar routes, ships at sea, emergency services, and systems that still depend on long-distance radio. The modern world may feel completely digital, but radio is still one of its hidden nervous systems. We only tend to remember it when something stops working. Power grids are another concern, and this is where the sun's reach feels especially surprising. During strong geomagnetic storms, changing magnetic fields around Earth can induce electrical currents in long conductors, including transmission lines. These extra currents can stress transformers and disturb grid operations. NOAA states that coronal mass ejections can cause geomagnetic storms at Earth and induce extra currents in the ground that can degrade power grid operations. This does not mean every solar storm leads to blackouts. Most do not. Earth's magnetic field protects as well. Grid operators monitor conditions and warning systems exist. But the risk is real enough that space weather is treated as an important part of infrastructure planning. A star 93 million miles away can place a burden on equipment designed by people who would quite reasonably prefer their transformers not to have opinions about the corona. This is why touching the sun matters. The dangerous part of space weather is not magic, it is physics. If scientists can understand the physics closer to the source, forecasts can improve. The earlier we understand an eruption, the better we can estimate whether it is headed toward Earth, how fast it may arrive, how its magnetic field may be oriented, and what kinds of systems may be affected. Parker Solar Probe helps by studying the young solar wind and the corona before solar structures have had time to evolve across vast distances. NASA reported that Parker's close images and measurements help scientists understand where space weather threats begin, and that the data should improve space weather predictions for astronaut safety and protection of technology on Earth and throughout the solar system. That phrase, where space weather threats begin, is important. Space weather forecasting has always faced a problem of distance. We can observe the sun from Earth and from spacecraft, but many of the key processes occur close to the sun, in the corona and the young solar wind. By the time a disturbance reaches spacecraft nearer Earth, it has already travelled a long way. It may have changed shape, interacted with other streams, merged with another eruption, or rotated its magnetic field. Parker gives scientists access to earlier stages. It is not just watching the storm as it approaches our neighbourhood. It is watching closer to the place where the storm first forms. One of Parker's valuable contributions is showing how complex the solar wind is near the Sun. From Earth, the solar wind can appear like a steadier flow, but Parker found it to be full of switchbacks, sudden magnetic bends, bursts and structures. NASA's early Parker results described the solar wind near Earth as relatively uniform compared with the complicated, active system Parker observed closer to the Sun. This matters because the solar wind is the background through which solar storms travel. If you want to predict the path of a storm, you need to know the road. If the road is smooth, predictions are easier. If the road has currents, bends, turbulence, traffic, and the occasional magnetic surprise, then the forecast needs better information. Parker's more recent close views have shown coronal mass ejections interacting near the Sun. NASA reported that images from Parker's record close pass showed multiple coronal mass ejections colliding in high resolution, and explained that when such eruptions collide, their trajectories can change, charged particles can accelerate, and magnetic fields can mix, making effects potentially more dangerous for astronauts, satellites, and technology on the ground. That is a crucial point. Solar storms are not always single neat objects moving through clean space. They can pile up, merge, compress, and reshape one another. A forecast that treats them too simply may miss the way their combined structure changes before arrival. This is not only about Earth either. Human exploration is moving outward again. Astronauts travelling beyond low Earth orbit, toward the Moon and eventually Mars, will not have the same protection that people enjoy under Earth's atmosphere and magnetic field. Solar energetic particles can be hazardous to crewed missions. They can arrive quickly and raise radiation risks for astronauts. NASA has emphasised that understanding high-energy space weather events is important for astronaut safety during future deep space missions to the Moon and Mars. In that sense, Parker is helping prepare not just for technology at home, but for human activity beyond the safest shelter of our planet. It helps to imagine future space weather forecasting as a chain. At one end is the Sun, with magnetic fields twisting, reconnecting, opening, closing and releasing plasma. Then comes the corona, where eruptions expand and the solar wind begins. Then interplanetary space, where the wind carries structures outward and storms may merge or change. Then near-Earth space, where monitoring spacecraft detect incoming conditions. Then Earth's magnetosphere, ionosphere, satellites, power grids, radio systems, and navigation networks. A weakness anywhere in our understanding of that chain can reduce warning accuracy. Parker strengthens the beginning of the chain, which is often the hardest part to measure. This does not mean Parker alone will make space weather perfectly predictable. The Sun is complicated, and plasma physics has a way of keeping scientists modest. Parker is one mission among many. It works with solar observatories, coronagraphs, heliophysics missions, ground-based instruments, and operational forecasting centres. NOAA's Space Weather Prediction Centre provides products and dashboards for communities including aviation, electric power, emergency management, GPS, radio, satellites, and aurora observers. Parker adds close to the Sun measurements that can improve the physics inside the models those communities eventually depend on. It is not the weather forecast read aloud at breakfast. It is part of the science that makes tomorrow's forecast better. There is also a larger lesson here about warning systems. A warning is useful only if it arrives with enough time and enough clarity for people to act. Satellite operators may need to put spacecraft into safe modes, delay maneuvers, or adjust operations. Airlines may reroute polar flights or change communication plans. Power grid operators may monitor induced currents and manage equipment carefully. Astronaut mission planners may schedule activities with radiation risk in mind. These actions are not glamorous. They do not look like a spacecraft diving through the corona, but they are the quiet, practical result of understanding the Sun better. The final purpose of exploration is sometimes a calmer control room. The public often thinks of space science as something far away, and understandably so. Telescopes show galaxies, rovers explore Mars, probes pass Jupiter, and the distances can feel almost decorative in their vastness. Parker Solar Probe is different because the science points back toward us. The Sun is close by astronomical standards, and its behaviour has direct consequences for Earth. Studying it is not only an act of curiosity, it is part of living on a planet inside a star's extended atmosphere. NASA's Parker mission page puts this plainly by saying that we live in the Sun's atmosphere, and that Parker's data will be key to understanding and perhaps forecasting space weather. That phrase can sit with us for a moment. We live in the Sun's atmosphere. Not in the dense glowing layers, of course, and not in the corona itself, thankfully, because that would make gardening difficult. But Earth moves inside the heliosphere, the vast region shaped by the solar wind. The Sun's atmosphere, in its thinnest and most expanded form, reaches across the planets. We are not separate from our star. We are embedded in its influence. Daylight is only the most obvious part of that relationship. Parker's achievement is therefore not a conquest of the Sun. It is not humanity defeating a star, which would be an ambitious and frankly impolite goal. It is humanity learning to read its star more closely. The spacecraft crossed into the corona and found that the boundary was uneven, that the young solar wind was full of switchbacks, that slow solar wind has different forms, that eruptions can collide close to the Sun, and that magnetic structures may recycle material back toward the star. These are not just scientific curiosities scattered like interesting pebbles. They are pieces of the larger problem of how the Sun transfers energy into space. And the more we know about that transfer, the better we understand the risks. If switchbacks help power parts of the solar wind, they matter to the background flow that carries disturbances. If different kinds of slow solar wind behave differently, they matter to the conditions that can build geomagnetic activity near Earth. If coronal mass ejections merge and change direction near the Sun, that matters to predicting whether Earth, the Moon, Mars, or spacecraft in between will be affected. If some magnetic material falls back after an eruption, that can change the shape of the solar atmosphere and influence what happens next. NASA reported that Parker's observations of solar material falling back after an eruption reveal new details about how magnetic fields responsible for space weather escape from the Sun, and sometimes do not. All of this gives the Sun more texture in our minds. The old image of a simple bright disk is useful for a weather forecast and a sunrise photograph, but not for protecting a technological civilization. For that, the Sun has to be understood as a magnetic system. It has cycles. It has active regions. It has eruptions. It has a wind. It has a corona that is hotter than expected and more structured than it appears. Parker has moved human knowledge into that structure. It is sampling the environment not after everything has travelled to us, but while the solar story is still close to its first sentences. There is a comforting humility in this. We cannot stop the Sun from erupting. We cannot smooth the solar wind, untangle magnetic fields by hand, or ask a coronal mass ejection to take a slightly different route because the satellites are busy. What we can do is observe, understand, model, prepare, and design. We can build spacecraft that survive close to the Sun. We can build forecasting centres that monitor conditions. We can harden satellites, protect astronauts, train operators, and create procedures for storms. We can learn the habits of our star, not perfectly, but better. And perhaps that is the real meaning of touching the Sun. It is not the reckless touch of curiosity ignoring danger. It is the careful touch of measurement. A spacecraft extends our senses into a place no human can go. It feels magnetic fields with instruments. It counts particles. It watches eruptions. It sends home data that slowly becomes knowledge. That knowledge becomes models. Models become forecasts. Forecasts become warnings. Warnings become action. Somewhere at the end of that chain, a satellite is protected, a route is adjusted, a grid operator is ready, an astronaut mission is planned with more confidence, or a radio user understands why the signal has faded. The touch becomes protection. The sun will continue to rise as it always has from the human point of view, though of course it is Earth that turns us into morning. It will continue to warm fields, power weather, feed forests and brighten kitchen floors. It will also continue to flare, shed plasma, twist magnetic fields and send particles outward. Parker Solar Probe does not make the sun safer by changing the sun. It helps make us safer by changing what we know. So after this long quiet journey, from the old dream of reaching the sun to the spacecraft that finally entered its corona, from the mystery of the hot crown to the birth of the solar wind and the storms that travel toward Earth, we arrive back where we began, under the same star. The sun is still too bright to stare at, too hot to visit, too large to imagine comfortably, and too important to ignore. But it is a little less distant now. A small spacecraft has flown through its atmosphere and returned with news. Not a simple answer, not a final secret, but something more useful and more lasting. A closer understanding of the star that makes our world possible, and a better chance of protecting the world that lives beneath its light. And wherever you are listening from, whether it is morning outside your window or late enough that the room has gone quiet, the sun is still there on the other side of the planet or beyond the edge of dawn, turning, glowing, breathing its wind into space. Parker is still part of that story, circling through heat and shadow, gathering measurements from a place that once belonged only to myth, eclipse and imagination. We reached out not with a hand, but with a spacecraft. We touched the sun, and what we found may help us keep the lights on here at home.